Oh, okay. Then I'll run out of board. Harder, harder. Good morning. Welcome to the first session of the second day of the conference. It's a great pleasure to have Professor Arvind Nair here. He will speak on T modules on flag varieties and extensions in some categories of representations. Okay. Thanks, Alok. So yeah, I realize I changed my title a bit, but I'll say why in a moment. Okay, so first of all, I thank the organizers. It's a pleasure and an honor to speak at this. I thank Kapil for turning 65. And I should say that although I'm going to speak about something which is sort of related to representation theory, but the idea is that it's a geometric computation of something that is of interest in representation theory. And it'll use D modules on flag varieties. So this is not, of course, a profoundly new thing. But I'll just mention that I first started learning a little bit about D modules in 2000. Kapil organized a thing on motives, or Nori's motives at Math Science. And in fact, Srinivas was there, Kapil was there, Madhav was there, Rajan was there. Yeah. And Kapil lectured on D modules and mixed order modules. Yeah. And so I began to learn a little bit about D modules then. I don't say that I learned much, but I tried. But then later I went back to TIFR and I tried to subjected other people to my lectures about D modules, of whom one was Nitin and was very useful to me. So he's not yet here. So in some sense, this is, but then I never used D modules again after, okay, I used mixed order modules, but now. So thanks. Okay, so the title also should sort of vaguely remind some people who have thought about exceptional collections in the sense of Beilinson, of that famous paper of Beilinson called Coherent Sheaves on Tn and Problems of Linear Algebra. And I'll explain why at the end. Yeah? There is a relation to that. It's not anything great, but it's there. Okay, so roughly speaking, I have there will be three topics. So represent are available and particular computation of extensions in a certain category, which I've introduced. And that category, this computation will be done by geometric means. And the third point will be an application of sorts to coherent sheaves. Okay, and this will be somewhat sketchy on some generalized flag varieties. Okay, so I'm not sure, I give some details, but maybe not awfully too many details about that, but somehow this. Okay, so the basic setup is the following. G is, so I'm starting with one, let's say. So G is a connected reductive group. And it's over, we'll take it to be defined over the real algebraic group, defined over the real numbers. And associated to this, we have the following. We have the Lie algebra of GR, complexified, let's say. Okay, so it's a complex Lie algebra, modulo it's reductive or almost semi-simple Lie algebra. And inside the real points, we have a maximal compound. Okay, and I think I'll just take it as given that this is the fixed points of a certain involution, the Cartan involution. Okay, so example to keep in mind is SLNR and the involution minus X transpose, and it fixes SON. Okay, so that's one example. So theta is an involution. Okay, so there is a notion that came out of the work of Harish-Chandra of GK module. Okay, so that's basically you have, say, V, and you have an action of G, and this also gives you an action of this. I'm going to also use the universal enveloping algebra. Okay, so that's basically all polynomial expressions in things like G acting as the central operator. We also assume that there is a K action. Okay, so the K action must be such that
when you differentiate this action, it will be the same as the action given by the inclusion of the Lie algebra of K inside the Lie algebra of T. And you need some more comparison. Okay, so I think this is, I'll just write down what the equation is that, add K, apply to say X, apply to a vector V in the representation, must be the same thing as applying K inverse to the vector, then applying the Lie algebra element, then applying K. Okay, so X belongs to. So the point is, this is an algebraic, and we assume that as a K module, it's a direct sum of finite dimensional representation. Dimensional K representation. Okay, so there is a finiteness condition on that. Okay, so this is the notion that came out of the work of Harish-Chandra from the, in the 50s, I think very early in his work. I'll just say that, make a remark that he said that, the natural representations on locally convex, complete locally convex topological vector spaces, it doesn't matter what they are, in particular Banach space. This gives rise to a GK module by differentiation. And the idea is that this should algebraize many problems to do with harmonic analysis and the representation theory of T. And so one takes as just given that there is a good algebraization and just works with the GK module, and it does reflect. So for example, there is a functor like this and it reflects irreducibility. So something is irreducible if and only if corresponding algebraic gadget is irreducible. Okay. So these things form an abelian category. And let me say that work of action that shows that there is fundamental abelian. So the natural thing is that you can ask what are the irreducible, and you can ask what are the extended. This is certainly not simple. Okay, so this is what you would like. So extension to be irreducible. And essentially, the work of Harish-Chandra in the 60s and 70s and the work of Langlands gave an answer to the first question. Right? And there's a lot of analysis tied up in the answer at the first stage. That is, that you have to say that they belong to a certain submodule category, which are this thing. But more or less, the answer was known by maybe the 73, 74, something like that. And the extension problem was not maybe so interesting then, became interesting later, and I'll say something about that. But that is substantially understood, let's say. Yeah. Much is understood. Certainly not in ordinary. Okay. But the point about the irreducibles is that there is a list or a way of parameterizing the irreducibles. Okay. So one thing is that, as we all know, that in particular, this is a UG model. So this is the universal enveloping algebra of D. So any GK module is also a UG module, and UG has a large center. Okay, this is by definition the center. And the center of UG was again understood by Harish-Chandra in the 50s. And it's fairly by just abstract principles, there's no extensions between two modules if they have a central character, if center acts by a character and the character is different. Okay? So the point being that extension problems between irreducibles, you should reduce to having a fixed central character. So I'll mention that earlier and later. And then the second question is, okay, so maybe I should mention here. So I need to have a slightly smaller category. So these are not also good, but Harish-Chandra introduced what came to be called the category of Harish-Chandra module. Okay, so I'll say what these are in a moment. Actually, I'll just say now. These are the finite length, the modules which are of finite length over UG. E modules plus finite under the center. Finite under the center means finite under the center. Okay. So inside the abelian category of all GK modules, which are easily defined, there is a slightly more subtle category, which is those which are finite length as UG modules, and they are Z of G finite. Okay. So these will be called Harish-Chandra modules. So it's a Harish-Chandra that all the So he was interested in this category and then he classified the irreducibles. But it's also true that between irreducibles, the extensions here will be the same as. So you might ask why am I introducing this category? It's why a larger category. Okay, so I need to just for the sake of I'll restrict to the simplest case. So as I said, you want to fix a category character for the center. Now there's an obvious character for the center in the documentation. Okay, then we just the map of this algebra, and essentially I'll call that epsilon always, and I'm going to fix that I'm going to look at only modules for which this center acts through the augmentation and Harish-Chandra modules for which the center acts through the augmentation. The point being that the general computation which one wants to do reduces to this case using standard technology. Okay. So these are the things. Now I want to introduce one more. There'll be several definitions. It will be a couple of steps deep, but it's essential for what I want to say. So the other thing is that we are not going to try to compute. This is a hard problem. As I said, the classification of irreducibles, I'll tell you how the classification was redone later very shortly in algebraic geometric terms. But the extension problem, I don't expect that, it's a difficult problem. So one doesn't expect to give closed form answers for, you would like to compute X, all the X groups of V up to that. And you can't give closed form answers because the general problem involves the Karzan-Lustig business, whatever that is. But I want to say that actually I'm going to restrict to a class of modules, which are at the moment, at least the ones which are of most interest for automorphic forms and number theory. And for those, you can give a complete answer, and I'll mention that. Okay. So I'll come to that in a moment. So that class I'm going to now introduce. These are the so-called cohomological vectors, which we can just define to be the representations V such that they are in the block in the usual sense of the trivial representation. Okay, this is the definition of the word cohomology. Okay, so it has some kind of X with the trivial representation. Okay, so of course the trivial representation has the right infinitesimal character. Okay, so and inside, okay, so okay, yeah, something, yeah, in the block of in the sense that so there is some non-zero. So this can only appear in degrees between 0 and the dimension G mod dimension K. There is duality and all kinds of nice things. It's a very nice setup, but basically I'm going to take this. Okay. Now, as I said, part of the motivation for all these things is the theory of automorphic forms, which lives on, which looks at representations on spaces like that, which are intrinsically unitary. Okay. So for the theory of automorphic forms and number theory, really what one is interested in is unitary forms. So I'm going to give that a name. So this is unitary representations in this case. Thank you. Yeah. Actually, irreducible. Actually, I'm only really interested here also, but yeah, maybe irreducible. I'll put here. Thank you. Yeah. Okay. So these are the ones which are of relevance to number theory and automorphic form. Okay. So now the problem in this whole theory. So Harish-Chandra's original goal was to understand the all unitary representations, and so his first step was to classify them without that, this weaker condition. And that unitarity problem in some sense is solved now, but it's solved only in an algorithmic fashion and doesn't have a good answer. But for cohomological representation, it does. Okay, so now I've further restricted myself to saying that I will only be interested in computing X between irreducibles or between two elements of code. So for B, W inside this, what is X star? Okay, so I might stop writing the GK because it's tiny conjecture. Okay. Okay, and I'll give you some motivation later, the vague motivation for why you do. Okay, so, okay, great. So as I said, all irreducibles here already lie in here, and computing the X in this abelian category is the same as computing in this abelian category. We'll sort of implicitly that we behind. Okay, so then the next step is to. Okay, so I should say, of course, I mean, this is relevant because, so the first construction of okay, so I should give you two examples. So I'll put them here and then I'll erase them there. So first of all, the trivial representation is going there. Okay, and I'll say what this is a little later. Okay, so this is certainly non-zero. And the second thing is that there were these representations which were constructed by Harish-Chandra. I mean, this is maybe the pinnacle of his work, which are the discrete series representations. And they have the property that xc phi is not equal. Okay, so I have to say with central character, GG character equal to. Okay, so these are kind of the two. These are somehow, in fact, this is actually equal to C in one particular degree. Okay, minus the one correctly. Okay, but anyway, it's non-zero. So this contains some interesting representation. The trivial is maybe not so interesting, but it contains the discrete. So that. So okay, then about some fast forward a few years, and Beilinson and Bernstein realized that you should geometrize everything. For those who are familiar, it's very much in the spirit of the Borel-Bott-Way theorem, and in fact, it contains it in some sense. So they said that let's look at the flag variety of the complexified. I'm not going to. Okay. The point being that now we also have the action of the maximal compact group K. Okay. And I'm going to complexify K because we want to deal with algebraic groups. So what we have here is a projective variety with an action of a certain algebraic group. Okay. And the maybe key observation that they made was that if you look at the space of global differential operators on X, so these are differential operators in the trivial one. Okay. Differential operators from O to O, this is actually equal to UG, okay, modulo the kernel of the augmentation ideal generated by. Okay, so this is a two-sided ideal because this is central. Okay, so this is that. So immediately you see that any UG module with this infinitesimal character, with this augmentation character, actually comes from a. Oh, sorry, you go the other way. Any D module, DX module, immediately gives you a module for this. Okay. And they proved the remarkable fact that actually you can go back. So they proved the following Beilinson-Bernstein equivalence. Okay. So I did not use this notation before, but it should be clear. These are GK modules for which that augmentation is the central character. GG acts through the augmentation. And they defined a pair of functors, which I will define in a moment. And they said this is equivalent to the category of D modules. So these are KC equivariant D modules, DX module. So DX module. Okay, so just as a note, these are assumed to be OX quasi-coherent for those who are worried about it. D modules for me will always be OX quasi-coherent. So what is the functors in each direction? For a K equivariant D module, okay, so K equivariant D module, you have to say what it means. It's the obvious thing, it works fine, just like K equivariant coevalent sheaf and all that, right? Just, I'll assume you're familiar with that. If you have a K equivariant D module, you take the global sections, it will be a module over the global sections of D itself, which is this, which means that you're landing here. Okay, that is, it is a GK module with the, okay, I'm fudging some things. That's the G structure. There's a K structure also because this is equivariant. Okay, so that's it. In the other direction, given a module V, I can tensor it over this global sections guy with dx. This is the functor in this direction. Just okay, like in FAC, like Sarah did for affine schemes, right? Basically that equivalence. And the point is that the proof of this theorem is essentially proving that the higher cohomology of dx always vanishes. So x is d affine. Okay? And more or less this drops out. Okay. So this is the Beilinson-Bernstein geometrization. And what is the point now? The point is that this is actually a very, okay, so there's one more step. Under this, I'll just say this, Harish-Chandra modules of that infinitesimal character become equivalent to coherent, decoherent D-mod. Okay, so these are coherent, decoherent, not coherent. Okay, so, but now there's a small miracle that dx coherent k equivalent D modules. Okay, so I should have said this at one point right in the beginning. So this, I said KC act, and this has finitely many miracles. And this is somehow there are two miracles that make all this work. One miracle is the fact that the higher cohomology of the sheaf D vanishes. The other miracle is that K acts on the flag variety with finitely many orbits. Once it acts with finitely many orbits, necessarily there are closed orbits and there's one single open orbit. Okay, so we'll come back to that. But the miracle that happens is that because of the finiteness, these objects are already regular whole moment. Okay, whatever that is. So that means that this is actually equivalent to a category of KC equivariant over C. On X. Now, Power sheaves on X are very big, simple objects. It's a fancy name, but in the end, the point of the power of the series is that they're very concrete objects. So that means that the irreducibles in this are basically classified by a pair consisting O and tau, where O is a KC orbit in X, and tau is basically a K equivariant connection on O. Okay. So if you, so this is like a which translates into a representation of a certain component group, which is that I take the stabilizer at any point in G, which is a Borel, so for X in O, and then I intersect it with with KC, right? This is the stabilizer of the K orbit, and then I look at the component group. So this is a representation of this finite group. Okay. So what is the point? The point is that the irreducibles, so just by just geometry and the geometric this thing, we are forced to have a certain, I mean, we get a certain parameterization of the irreducibles. Okay. So it's again, it's the pairs consisting of a KC orbit, a KC orbit and a KC equivariant connection on the orbit, which amounts to a representation of a certain finite group. Okay. So in particular, there's the trivial representation of it that we can take here. Yeah. The KC orbits, yeah. Yeah, but the KC, it's KC equivariant, right? So the supports are orbits. Yeah. It is based on an orbit, and then it may be an IC extension, or it will be some kind of perverse extension to it. Okay. The other magical, one more magical fact that happens is that the inclusions of the orbits in X are affine models. So that means that the ordinary push forward is again perverse. Or the ordinary push forward of the D module is a D module, regular number. Okay. So this is actually, this is actually a really, this plays a really important role because this is actually a refinement of something that in the Harish-Chandra-Langlands classification, some things are left a little, okay, it's slightly different. This is a slightly stronger thing than was there in that, and it's very useful. I will mention how it comes up for me. Okay, so this is the Beilinson-Bernstein localization. So it's translated into this thing. Okay, so now I'll mention, okay, so there is some work to be done. This is an equivalence of categories, Billing category. Yeah. So everything is exactly the same. Yeah. Up to the whatever. So, and these are the irreducible objects. They are parameterized by a KC orbit, and yeah, so this would have to be irreducible. Like yeah. Irreducible Harish-Chandra modules, right? So yeah, I mean, that's the one can understand them. So for example, okay, so since you asked, one understands them through the Langlands classification, right? I mean, one represents them as quotients of something. That's about. It's a labeling and it's not clear. Yeah, it's difficult to. It, it causes problems, yeah, which are interesting, of course. But yeah. So the point is here, this is in the end all very simple. The simple object. Yeah. It's just a pair consisting of orbitals. Okay, any regular central integral regular central character is okay. Actually, any regular central character is okay because the non-integral ones are actually very degenerate, very easy. Again, using this, you can on this side you will basically get very few objects. But for any integral one, you can use translation functors to get to this. So that's it. Singular is another question. Singular level character. I will say something at the end of this time. Okay, so the question now becomes, so I had sort of said I want to compute this, right? The question was this. And so I need to know the place of these representations in this classification. Okay, and that's an easy consequence. So, I mean, this is not somehow written down anywhere carefully, but okay, I mean, it's a straightforward consequence of a theorem which was proved of Heck. Okay, I won't write all the names. It's Heck, Milicic, Wilfred Schmidt, and Wolf. Is that, so I'll just say the homological representations, which always means now this representation, let's call them big four representations, are of a special form. Okay, so I'll tell you what this form is. Okay, so I have to give you an orbit and a representation of the isotropy group of the action at that on that orbit. That is the isotropy group. The tau will be trivial, so that's not good. So the main point is get the orbit. So here we actually see something which was, I did mention that these were originally introduced by Parsati. Parsati, I did mention. Oh, sorry, okay. Okay, yeah, I started thinking about this. But of course, homological representation, the first construction of what turned out to be the final list was done by many of our former colleague Parsati. And he constructed them by hand, so to speak, the GK modules by hand in a very complicated fashion. Later, this was generalized by Zuckerman to give a functorial approach. And then it got subsumed in the geometric theory using what I'm about to say. Okay. Right. So the pioneering work in that matter was done by Parsati, who defined the following notion of a theta stable parabolic. Okay. So this is a parabolic of the complex group such that, so remember that like just think of SLN and minus X transpose. That's it, right? So you need to have something which is got the property that stable and P intersected P bar. Now this bar is with respect to the complex GC, right? The combination of entries. This is the Levy circle. So these are the parabolics which are sort of most opposed to the real being a real parabolic. The other extreme from being a real parabolic. They're in exactly the opposite direction. So Parsati introduced this definition. And then what happens is that you have a natural map from the flag variety to G mod P or G C mod P. Okay. And I'm just going to tell you that we know how to parameterize the closed orbit. Okay, let me just, this diagram will be of some importance, so I should write it here. Okay, so this is O tau. Okay. So you have X, the flag variety, maps to GC mod P. Okay. Inside this, there are, okay, sorry, I apologize, but I want to do it this way. Okay. So inside this, there are certain closed orbits. Okay, so I mentioned that the flag variety has finitely many orbits somewhere, so that, and there's an open orbit, unique open orbit, and there are closed orbits. The same is true for generalized flag varieties of this type. And so you can just base change this. And this is a smooth subvariety, so this is a smooth object, K invariant. And this contains a unique orbit. It's the closure of one orbit. Okay. So that means that given any P like this, we have one distinguished Kc orbit, which actually has an extra property that its closure is smooth, because this is the Cartesian vector. So let's call this O sub P. Okay. So O sub P is equal to a Kc orbit in X with, and an aside is that it has smooth closure. Okay. But as I said, the dictionary says that orbits, pairs, orbit and representation give me an irreducible object. I'll just take this orbit and the trivial element. Okay. And that is the A parameterization. It's a redundant parameterization of cohomological element. So I should state that somewhere. So OP trivial, the corresponding simple object is a redundant parameterization of simple in the homological unitary representation. Okay. But redundant, meaning it over parameterized. Yeah, yeah. There will always be actually. Yeah. There are many P's, and if two different P's kind of have the same, two different P's can. No. This is the no, it's not. It's they should differ by a compact. So by the way, the orbit is sorry. Okay, so okay, this is not redundant. Sorry, if you just look at it as P comma something, it's redundant. So different P's give the same OP. That's clear because you see, I could have gone to a further some other P here, pulled back the closed orbit from there, and then further pulled back the closed orbit and taken the open orbit. Okay. So this OP is not redundant. Okay. This is clear. The orbit classification from Beilinson-Bernstein cannot be redundant. Sorry. As P varies, several P's will give the same orbit. So in fact, OP is not a good notation, and but I'm just going to get it, right? Okay, so now we have to compute X, right? So okay, so those are the closed orbits, and that's the localization. Okay, so as I said, the Beilinson-Bernstein localization, it fixes an infinitesimal character. Now, if you have a ring and you fix the central character, you can't compute X with that fixed central character because you have to allow the generalized character to be that, because extensions will look like this, right? Epsilon, something like that, right? And this will not be, this is not epsilon character, this is epsilon 1 minus epsilon nilpotent or whatever you call it, right? So this localization is not enough for to compute X. Okay, this is so you have to localize something better. Also, if you want to compute X here, yeah, so first of all, you need to go to the bigger category. Yeah, so actually I'm going to use the coherent version. Right. Also, you want to understand the derived category of this guy, right? That's what computing is among. So this problem, okay, I haven't got to this thing, right? Okay, so just to this thing, there is this parameterization in terms of geometry. We have translated the problem that we want to compute, at least the parameterization of list of things for which we want to compute the X into geometry using this observation. Essentially, this some work, a little work with the theorem of Heck, Milicic, Schmidt-Wolff. And now the question is, but that's not helping us because we don't know the derived categories here. Of course, the derived categories will be equivalent, right? I mean, so immediately. But actually, the derived category of this guy gives a wrong answer. So we have to introduce this generalized notion of generalized. So I'll just say that problem was solved also by Bernstein and Lund. And it, no. There are extensions, and in fact, there are. So for example, the X groups that we want to compute I suppose we know a priori that they are finite dimensional. Yeah. The X in this category are actually usually infinity. You'll see exactly why it was happening. Okay, so I'm going to use epsilon tilde to mean, so the subscript epsilon tilde means generalized character, GG character. Looks, Valerie, LUNTS. These are, I think, 19. These are all old results, around 1998. So this will be this thing. So I'm just going to write down the analog of that diagram that I had. So the derived category of GK modules whose generalized infinitesimal character is epsilon. Yeah. This becomes equivalent by the similar type of thing with the derived category. And then I'll just, so, okay, pardon me while I fix this, write this diagram and then I'll explain what the terms are. And this has a functor from the Harish-Chandra modules of that generalized infinitesimal character. Okay, so I have to explain. So this side is clear. I look at it's still an abelian category where the generalized infinitesimal character is epsilon. So that means that this just means that epsilon of Z to some power will kill B for all. So for all elements of the group of the module, there exists N such that. Okay. So that's what generalized infinitesimal character means. Okay. This is the Harish-Chandra module with the same thing. Okay. So there is this inclusion, standard results that are, people who have done derived category of coherent sheaves know that the derived category of coherent sheaves is the same as the derived category of quasi-coherent sheaves with coherent cohomology. Right? This is the standard term. This is a version of that. Yeah. So if the cohomology, if you impose finiteness conditions on cohomology object, then it's okay. This side I have to explain. So this is actually this is the category of KC equivariant EXR. So I have to define X tilde, right? So the main, a very important point is that X tilde is the following, that you have to introduce a new space, which is the enhanced flag variety. So it's just actually the quotient of the, so B is, I don't know, H times N. So the first point is that's different is that the derived version of the localization happens not on X, but on this cover, but that's okay. Yeah. The second, much more subtle point is that you need to know what it means to talk about an equivariant derived, K equivariant derived category of Bx tilde module. Okay. And sadly, not sadly, but this is not the derived category of K equivariant Bh module. Okay. This requires a completely separate definition. Unlike the coherent case, where derived category of equivariant coherent sheaves is the equivariant derived category, in this case, there is it's much more complex, right? You have to look at all resolutions of this as space and set up something. Okay? So this notion was defined by Beilinson, Ginsburg, and then later Beilinson and Bernstein and Bunz worked out all the details. By the way, this is true in motives also. I mean, if you want to define an equivariant category of motives, you can't do the naive thing. You have to do some that has recently been done by. Okay, and this is the coherent objects in that, or objects with coherent cohomology. And this inclusion is again, if you want to compute the X between two objects here, you can go here and do it. And similarly, if you want to compute the X between two objects here, you can go here and do it. That's just some finiteness type statement. Okay, but now the point is that this has translated the problem into a topological statement. I'll say why. So there is the Riemann-Hilbert correspondence, which I implicitly used here when I said that D modules are the same as Fourier sheaves. That was the version of the Riemann-Hilbert correspondence. So here you get that the Riemann-Hilbert correspondence maps this to constructible sheaves on X tilde. Okay. So I'm forgetting a little information what this epsilon was. It doesn't matter. And this is no longer an equivalence, but it's fully faithful. Okay. Fully faithful. Okay. So again, what does this mean? This means the K equivariant derived category of constructible objects here, which is again that definition of Bernstein and Lund-Feisel. You have to look at, okay, so just for those who, this thing, it's like looking at the Borel construction and the derived category of the Borel construction, but you can't really do that. So you have to filter the Borel construction in a nice way, construct an approximation, and you know that EK has to be approximated by finite dimensional objects, and there's a mess. But for a space with an X action, you have this space, right? Yeah, so that which gives equivariant cohomology. You can take it for anything, but here there's not much difference between taking K, the compact, and its complexification. Everything works kind of the same. Here we can take K to be compact. Okay. Okay, so what is the point? The point is that the upshot of this thing is that provided I know this one, Kc, comma C, constructible. Yeah. But constructibility is a relatively simple. You don't even need to put that. I mean, it will still be a fully faithful form. So I mean, but I just okay. So what is the upshot? The upshot is I want to compute an X between two irreducibles here. I think of it here. I go over there. I apply that, and then now I'm in a computation in topology. Okay. So the upshot is that this reduces any more or less computation of X V for irreducible to a computation in equivariant topology. Okay, so let me give an example just so that you'll get the flavor of it, and then I'll state a result that you can prove using this, which will sound abstract, and then I'll try to make it more. Okay, so okay, so of course the most important representation is the trivial representation. Okay, and so one should compute that. Okay, and the answer is the following. So by this yoga or whatever, this is the same thing as the forms in this category, let's say. Okay, this thing of the constant sheaf on X with the constant sheaf on. So I didn't emphasize this, but in this dictionary, obviously the trivial representation has to be something trivial. It's just the constant sheaf on X. Okay. So this is the form in this triangular category. Okay, so that's not much use, except that actually this is just the same thing as the ordinary equivariant homology of X tilde with respect to the compact cube. Okay, so this is the Borel equivariant. This is the definition of this guy. EK crossover plate. Sorry? Yeah, so this is a. It's not an internal norm, but it's the total norm. Sure, yeah. So it's the total norm. Okay, so that's something. Okay, and now this is something that one can compute very easily, and I'll say what it is, and it's simply the cohomology of the what is classically known as the compact dual symmetric space. So every real form, every real group sits inside its complex group, and somehow it has a compact form. This is an ancient theorem. This is very well known due to Hermann Weyl, that given any real group sitting in complex group, there is a canonical form, which is the compact real form. Okay, there's a compact algebraic group sitting in G such that they have the same complexification. So this is GU, and K is the same old K. Okay, so this is a symmetric space, a classical compact symmetric space. Okay, and so this is just a easy exercise more or less. So notice that these X are finite dimensions because this is just a compact space. Had we actually worked in this wrong category without allowing influential character, here we would have got the equivariant cohomology of X itself. Okay, and that becomes free over BK. And it's not finite. Okay, anyway, that would be the wrong calculation, so we should do it. Okay, so what's the point? The point is that, okay, so I gave you the trivial case of the calculation. The general calculation is just actually kind of a souped up version of this. So I will not go into that much, but I will state a certain result. There will be some two terms in the result which I have not defined, but then I will give an example and an application, as I said, to algebraic geometry, which will at least give you a flavor of what those terms mean. Okay, so I hope that will be. So in the general case, oh, I should say that, yeah, okay. I should have said it some time ago that, okay, when I state the next theorem, I'll say it. So it's a fact that actually this guy, okay, so maybe this will be a, surprisingly maybe, so in a paper we wrote a little while ago, Deependra and I computed the total dimension of this thing. And it has a somewhat surprising form, meaning surprising, not surprising. Okay, let me write it down first. Yeah, okay. So I'm going to be slightly unclear about what this means, but okay, so remark, and this plays a role in what I'm going to say, but I'll just say it now. Okay, so this was computed by Deependra and myself. This is for trivial, so I'll come to that statement here. So I'm just motivating it by saying that these terms come up. So what is this? So this is just the, okay, so what we choose is we choose inside G a maximal torus, maximally compact torus. So now remember that we are in a real group, so there is a notion of torus can be compact or non-compact. We chose one whose compact part is maximal. So TC is of maximal dimension, and A is the split part. So A is split part, and TC is the compact part. And this while group is the absolute while group of G. Theta is the involution which acts on the characters of T. So you can ask for the things which commute with theta. And this is the while group of the compact group K. Okay, this formula is slightly off, but I don't want to get into the technical details. There's this, you have to adjust it's likely to be exactly true, which is understood. But the point is that this is a very nice computable thing which should have been computed in the 1940s or something like that. But apparently it is the case with dimension A being non-zero, we didn't have it anyway. Okay, so what is the point? But that constant, I wanted to introduce that constant because it's important. So now I'll state this following theorem, which seems to control X, and then I'll try to get some algebraic consequences of that. Okay, so there is the following theorem, and I'll say some more. Okay, so now there will be a term which, well, several people in the audience know, but I'll explain what it means in some hand-wavy fashion for the rest. So A packets phi1 and phi2 of representations in cohomological unitary representation. So these are finite subsets, okay? Prescribed finite subsets of some kind. The sum over phi1 in big phi1 and phi2 in big phi2 of the dimension of X of phi1, phi2 is a constant unit, is this universal constant. Okay. Okay. So I have to say something about what this means. And by the way, a degenerate case of this theorem is that phi1 is the singleton, the trivial representation, phi2 is the singleton, the trivial representation, and then I'm saying this. Okay, this calculation. But the point is that this equivariant setup essentially allows us to compute this group completely. I mean, you'll believe that what I described translates into a problem in topology, and that problem in topology is very easy, right? So we compute it. So this can be computed, and it's sort of like I mean, I don't know. You could say that these finite sets. So part of the problem is that these finite sets are supposed to exist and have certain properties, but they don't have characterizations as such. So this is a property that tells us that they actually have some property. I don't claim it's a characterizing property. Okay. I'll mention the relation to exceptional collections in a moment. Okay. So before going on, let me make some remarks. Oh, yeah, sorry. So when I say dimension of something x star, I mean the total dimension graded. Yeah, so this is maybe some over I. So when I write dimension of a graded object, I mean total dimension. It's not an Euler characteristic. This is an important point. Somehow, so because it's not an Euler characteristic, it's a simultaneously upper and lower bound one. You know, it's some sort of conservation law. Okay. So one remark is that this can be reinterpreted as computing something called, okay, so maybe this remark, I'll just say it out loud. It appears that this computes a certain twisted elliptic pairing between certain packets of representation. One can appeal to results in the literature to say that this is what, because the twisted elliptic pairing has this, is like this side. And so we are computing something. I'll mention this later. The other point is that, so this is, maybe there's a relation to harmonic analysis. And I mean, yeah. The second thing is that there is a p-adic aspect to all this, which I am saying nothing about. Okay. Which is roughly speaking that these homological representations are representations of the real group, but they can naturally be put into global automorphic representation. Then you can do vary things with that. You can fix a prime P and vary the Hecke eigenvalues p-adically at P. And in that context, this quantity appears to, at least in some examples, give some sort of dimension of space of p-adic automorphism. And the fact that it's independent of the pi1 and pi2 is something, it appears to have to do with something called the eigenvariety being connected, which is a general conjecture or expectation. Okay? So all these things, unfortunately, eigenvarieties, A packets, all these things are a matter of defining them correctly at this stage. So one can't state a theorem as such, but it supports the idea that those are connected. Okay, so I'm not going to say anything about this. The third part is that there is this, as we mentioned earlier, there is this Langland's parameterization of these objects. And that says that actually for A packets, they have a related thing called an A parameter. And the A parameters of homological representations, Deependra and I had worked out a few years ago. And in fact, there's a nice interpretation of this formula in terms of the A parameter. Okay, so which won't surprise you, but anyway. And that is, so there is can be interpreted in terms of the Langland's duality. Let's just say that. And it gives evidence for some conjecture which one might make, which might be too much more generally, but it's probably very hard. Okay, so now I have sadly only 5 minutes. Oh, I forgot to say that. Thank you. So in the case pi1 is trivial. Pi1 is the trivial representation. This formula was proved by Deependra and me in a paper which appeared in the 2021. Yeah, sorry. So it says, in that case, it says something concrete. It says that, so if one of these is just taken to be the trivial representation, and that is in itself a packet, okay, I should have said that, then basically you're summing only over one packet of the dimensions of certain cohomology groups. And that was a formula that we found proved earlier. But I should say that our approach to proving that formula becomes really, really complicated for this one. for the two variable x pi 1 pi 2. So the geometric thing is much more big. That involved some Lie algebra cohomology spectral sequences and some fairly complicated inductive thing. And to be honest, I didn't work out that too finally because yeah. 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 So you take the case of the trivial packet and the trivial packet, it is that state. That's what I was telling you about, in the sense that if you believe the eigenvariety is connected, but there is a tricky point is to interpret this in some sense as the dimension of something on the eigenvariety. That doesn't seem to be possible that seems to require a lot of, I mean, I know that can be done in SL2 and a few other cases. There's something called Judith Ludwig who proved some theorems, which can be reinterpreted in that case, right? And then, yeah, you could deform to the trivial. So now you're asking interesting questions. So the explanation of this factor is really very interesting. So this is an exterior algebra on A, right? So why is there a dimension of an exterior algebra? Of this space. But this tends to be only in even degree. Not always, but only in even degree. No. So in fact, this fact is false for Euler calculus. Oh. Which formula? That formula. No. So I mean, this is just a remark. I mean, I should have said this is the minor thing in our paper. This is not the main point at all. Here, I'll tell you what to do. Okay, compute the Lefschetz trace of theta. Theta is an endomorphism of this trace. Theta acts by -1 in odd degrees and 1 in even degrees. So when you compute the Lefschetz trace, then you have to parameterize the fixed points correctly and check that the sign is +1. Yeah. And the point I mentioned this is that actually the general computation within our formalism reduces to that case. Okay, so I'm sorry, but okay, so I'm going to be very sketchy now. Okay, so there is a special case, which is the kind of most important case when the special case when GR mod K is complex, has a complex structure. So this is what we call a Shimura variety, or in this case, okay, so I've kind of given away, in this case, something I said there, du mod K is actually a flag variety, of a generalized flag variety, where P is the maximal parabolic stabilizing a minuscule force. So it's a special kind of maximal parabolic. Okay. So for example, if one takes UPQ or SUPQ to be G, then this will give you the Grassmann. And in particular projective spaces. If you take G to be the symplectic group, the non-compact symplectic group, this gives you the Lagrangian Grassmann. Okay. Now, in that case, by the way, this term goes away and this theta goes away. And so basically this right-hand side of this guy is equal to just the order of y group of G mod the order of y group of K. Okay. Now, this is usually a power of 2. Like, for example, in this case, it's 2 to the n. So now one can do the following, which is that you consider x tilde modulo K, Kc, which is the thing we've been computing with. Consider it, just take the stack portion. This has a map from, say, GC mod Kc. One can construct such a map. Okay. And this maps to GC mod P mu, because it's a fact that actually, I'll say that in a moment. P mu, sorry. And P mu is actually, as Levy is actually saying. This is just the setup that exists in this special case. Okay, so I've written this homogeneous things as stacked bucket, whatever. I just want to put brackets to be safe about it. This is actually an affine space fibration. Okay, so you can pull back objects from here. If you had coherent objects here, you can pull them back here and descend them to this. Okay, so what I'm trying to say is that if I had reasonable coherent sheaves, K covariant coherent sheaves here, I could get coherent sheaves on this object. Now, where do I get these objects from, right? So the point is that the D modules underlying representation are actually not just D modules, but they have complex mixed Hertz module structures. So they don't have a rational structure, but they have a polarization. Okay. So this is not, maybe I don't use this, but about 20 years ago, I think Srinivas and I were at a conference where Wilfried Schmid talked about their approach. Schmid and Villonen had an approach to the unitary dual. And they basically, first thing is to look at construct a theory of mixed Hertz modules with where instead of eigenvalues of Mondrian being roots of unity, you allow any thing of norm 1. So polarized things. And then the point being that all functorial operations can be done and you stay inside that. As it turns out, this geometric classification of Beilinson-Bernstein basically tells you that the things that you want to study in representation theory actually have complex mixed Hertz module structure. That means there is an extra F filtration, which means that you can take its graded and produce coherent object. Okay. So the upshot is that if I take the coherent objects, I take the discrete series packet. Okay, so this is the point where there are exactly this many discrete series. I take a particular graded F of the complex mixed Hertz module associated with that by Schmid, Villonen, and now it's all worked out by Davis and Villonen recently. I can descend it to produce objects in the derived category of coherent fields here. Okay, and these are exceptional in the sense that, so why are they exceptional? The point being that you see, I didn't say this very clearly, but the other extreme case is that these are both the discrete series packet. Okay, in that case, the discrete series don't extend among themselves at all. There are only Homs. There's no higher X. Okay, this is kind of like taking X between the graded pieces of the Hodge module associated to something where everything is vanishing. So since the F filtration, okay, so the E1 spectral sequence for the Hodge filtration always will degenerate in this instance. So from knowing that the vanishing of the whole thing, you can get the vanishing of the constituent piece. Okay, between the graded. So there's a point here that you have to take the correct graded in all the different discrete fields. So that's the working out technique. Okay. So the net result is that, and then you pull back here and descend here, and it will still be accepted. Okay. So I'll just say quick. Oh, sorry. So exceptional collection in the triangulate category of derived category of coherent sheaves is a bunch of objects with no X between themselves, between each other. And Beilinson proved that the derived category of Pn, there's O up to O1 up to On is such a collection, and it spans the derived category in the sense that it generates it as a triangulate category. This is a very famous 3-page paper of his 1970. Of course, very famous paper of Beilinson is highly ambiguous. But anyway, so after that, okay, so I'll just say in words. After that, many people, Kapranov extended to Grassmannian. Kuznetsov and Polishchuk produced for many more Gmod Ps, including many of the minuscule ones. But the problem is they use some tricks which produce non-canonical objects, and they're not able to prove the fullness. Okay, I can't prove the fullness. I mean, I haven't thought about it really. But what the point is that one is getting canonical ways to construct exceptional collections on this, and of the right rank. Sorry. They almost certainly do, because there are the right number of them. So if they don't, it would be some very perverse thing which shouldn't happen for flag varieties. So one can hope that they generate. I mean, I don't know. I haven't thought about whether one can use this to say something. But really, basically, the idea is that that they can be proved to be exceptional. And so, for example, for Pn, you will get back Beilinson's exceptional collection, or maybe maybe a shift of this. Yeah, with a minus sign. Yeah, right. And sorry, yeah. And you'll get all those. And I think the only new exceptional collection will be for the guy associated with E7, because Polishuk and these guys did a lot of detailed work. But I think these are better in some sense because the vanishing comes from a different place than they compute. E7 has a Schindler, right? So of course, this thing should work for all discrete series groups, but it's not clear what. I mean, the Gmod P is there always. This isomorphism is not there. So one is constructing this part of the diagram is okay. There's no way to get it, but it may not be impossible. There may be something to say. So, I mean, from the point of view of the maybe algebraic geometers in the audience, I didn't define A packets, but this suggests that at least in this special case, an A packet is a Lefschetz, what they call a Lefschetz decomposition of the derived category of coherence. Where that means that instead of individual objects, you allow some block. And I don't know if this characterizes the A packets in this case, I'm sure it does. Yeah. Yes. Yes, but this is, but see, the thing is somehow this, yes, this is a valid point. But the thing is that it still exists as a K equivalent object. It's not G equivalent. It's coming in the Hodge filtration of a G equivalent, G homogeneous local system, but they're still K. I mean, they correspond to the weight 1 for a cell. K weight 1. They exist. The coherent object exists, there's no problem, and I can construct it by doing this. Yeah, okay. Another thing which is, yeah, I mentioned some. There's, of course, the interesting thing would be to extend it to more. Okay, I'll stop. Sorry. Thank you.
Questions or comments?
Yes. But for UG, not for GK. For GK also, for the pair also, or for UG? For UG, yeah. So there is a. Yeah. So the thing is somehow I think that yeah. I think in the p-adic case, the flag variety is completely missing. Yeah. Rather, it is only the dual geometrization which exists, right? So therefore, I don't know. Yeah, that is true. So in this case, finitely generated modules. Sure. Yeah. Yeah, but yeah, but I mean, Deependra's question is more at the beginning. Yeah. No, so I mean, it'll be true that the derived category of finitely generated modules will be the same as the derived category of all modules, but with finitely generated cohomology. And so if you want to compute between finitely generated modules, you can just compute in all modules. That's certainly true. I mean, that's general kind of no-theorem type arguments, right? But anyway, these rings are not theorems, it's okay. But here the problem is that for general G modules, there's no localization to the same, there's no similar localization. I mean, you can localize because this basic theorem is there, right? In UG modulo kernel of epsilon UG, right? So any UG module can be localized. That's okay, right? But the objects in the D module category will not be, they'll have no finiteness property. So here you see because, I mean, you can still, yeah, you can compute things there. I mean, that's how the original cardinalistic conjecture in the complex case is proved, right? By localizing on the flag variety. Yeah, for all finitely generated modules. And no, but then you have to look at O, category O. Right? I mean, that is that category O of UG module. So I think perfectly general finitely generated UG module. I don't know that there's certainly no, the geometrization doesn't work, but I mean, I don't think, yeah, I'm not sure that people will. I mean, these BGG and all introduced category O because, well, it was nice way back when, and I think mostly people study that, but I'm not sure. It's possible that. Yeah, okay. Sorry, I'm sorry I went way over.
If there are no other questions, let's thank the speaker again.
Thank you.
Okay, so it's a great pleasure to have Professor Om Prakash Das from TIFR Mumbai. He is going to speak on recent developments of the minimal model program for Kähler.
Okay. Thank you for the invitation. It's a lovely campus. I woke up the sound of peacock, which is extremely exotic. In TIFR, we hear parrots, but yeah, that's not peacock. Okay, thank you for the invitation. Okay, so in the slides, I started a little bit differently. So I thought just maybe I change a little bit and just give a quick introduction to what a minimal model program is so that those things are more understandable. Okay, so let me start with a simple definition. So, yeah, so let X be a variety and D a Cartier divisor. D is called NAP. It's quite elementary, but just in case, it's called NAP if D intersected with every irreducible curve is non-negative for all curves C in X, all irreducible curves C in X. Okay, I'm going to use this term quite a lot, so I thought just to define quickly. And let me define another thing, which I call contraction. Sometimes it leads to confusion if you don't define properly. So the proper morphism let's say F between two normal varieties. My varieties are going to be almost always normal or sometimes even smooth. Is called a contraction. If something very simple condition, the whose part of the structure C is the structure C. Okay. And what it says is that if you have this property under when the two things are normal, I mean, I guess you don't even need normal, this is definitely implies that F cannot be a finite morphism. So there is a positive dimensional fiber. So something is being contracted here. Okay. It guarantees that this implies that F is not finite. It cannot be finite morphism. Okay. I need that. I mean, need that in the sense that whenever I say contraction, it's a genuine contract, something positive dimensional being contracted. Okay, so let me start with the very origin of minimal program, that is, sorry, yeah, okay, yeah. So to say this tape is not an isomorphism. It's just, yeah. So it's an isomorphism. All right, so let me start with the very sort of beginning of the minimal program and surface, so that Kapil Paranjape's theorem So minimal program is sort of an algorithm, theoretical algorithm. Don't have much to do with the computer programming, by the way, although the name suggests otherwise. Is that given a variety, can you reduce it to something really minimal? Okay, that's the name minimal. Let's see what it means for surface. This is around 1920s. I mean, this I'm sure the graduate students have also seen it in a Carson book or some other equivalent form. That let X be a smooth projective surface and C is a -1 curve. I'll define C is a -1 curve, i.e. C is isomorphic to P1, which with whatever base field that we are working on, and C square, the self-reduction is -1. Then the theorem says that there exists a birational morphism F from X to X prime to again a smooth projective variety X prime such that the f of C, the curve has contracted to a point now, and anything outside of this curve C is still isomorphic via this F. So let's call this one a point P naught, perhaps P naught, a point in X prime. Then X minus C is isomorphic to X prime minus the point P naught. We precisely contract that, and the target is still smooth projective surface. Okay. So this is sort of the beginning of neural program, and then you can from here you can clearly repeat this process that I start with the surface X, let's call it X naught, and you ask the question, is there a -1 curve? Is there a -1 curve? Okay. If not, then by Casanovas theorem, no will imply there is a contraction. Let's call it now X1. And you ask the same question, does -1 X1 has a -1 curve? Again, if sorry. Yes, sorry. I wanted to, okay, I went to them in my head to them, not F condition. Okay, yeah. Sorry, yeah, thank you. If there is a -1 curve, sorry. Then there is the contraction, and then again you keep repeating this thing. And what happens is that eventually this thing will stop. And the reason is that at each stage you have the Picard number is strictly decreasing. Rho of X1, rho of X0 is strictly bigger than rho of X1. It's a decreasing sequence, and every positive dimensional variety must have Picard number at least 1. Okay. So that means that after a certain stage it will stop producing, let's call this Xn equal to X star, such that X star smooth, projective, and has no -1 curve. This is what is classically known as the minimal surface. Okay, in this case, everything is surface, so it is here. It's a minimal surface, and then the idea is that you try to use other thing, for example, Ithaca vibration. You try to classify them and consider the modular spaces as far as you can go, for as explicitly as possible. So idea of the MMP is to start from here, and can you do these steps in higher dimension? In dimension 2, it was very convenient to have this Casanova theorem. And dimension 3, it was observed there is no obvious analog of Casanova's theorem in higher dimension. However, in the 1980s, Mori started making some revolutionary progress in this thing. So he sort of changed the question. So if there's a scenario, so if, for example, the canonical is pseudo-effective, then it is going to be unique. If it's not pseudo-effective, then even on certain level, it's not unique. For example, you can go to P2 and a line and 2 point on that block here. Okay, so here's Modi's idea that, so this was Modi's idea. So we as looking at this problem, this is around 1980s time. Okay? He was looking at this problem again. There's like a 60 years gap, and then what is the essential part of this thing? That there is a contraction when there is a -1 curve. So let's say C is a -1 curve, P1 and C square equal to -1. So see, by adjunction formula, you have this, the canonical of X. So yeah, this is contained in X plus the curve C dot C is 2 times the genus of C minus 2. So that sort of gives you, yeah, so this is P1, so this is -2, C is equal to -1. So the fact is just Kx dot C equal to minus. Okay. So necessarily, anytime there is a -1 curve, canonical is dot C, the curve is negatives. Okay, the number -1 is not so important, fact that this is negative intersection. Okay, so that means this one means that Kx is not net. That's what he said. So Modi changed the question. They instead of asking for a -1 curve, in general, if I ask whether canonical is net or not net, okay? So can I say something? Okay. So Modi's question. So yeah, this is now in any dimension, okay? Dimension of X is arbitrary. Okay. Arbitrary that if Kx is not net, does there exist a contraction? It's a sort of very vague question. Contraction of what? What can you can contract and everything? So he looked at it very systematically, actually. So his question, I think, originally wasn't exactly this. So he wanted to get something like, if Kx is not nef, then can you produce some interesting curve in X, for example, rational curve, okay? Because this is a rational curve. And so that is the first thing he proved, that if canonical is not nef on a smooth bijective variety of any dimension. So let me start the formal setting then. And by the way, these things all in arbitrary characteristic. I'll concentrate later on a complex number, but for now everything is arbitrary characteristic. So let's say X smooth projective, okay, and Kx not net, okay. So this is what Modi did here. Modi's famous, this is what he first proved. Now it is known as Modi's bend and break. Bend break technique. Then you can show that there exists a rational curve C inside of X. By the way, by rational curve, I do not mean it's P1, it's birational to P1. So C could be possibly singular. So maybe right here in parentheses, singular. Okay, if we normalize it, sure, it's no longer inside of X, but then it will be P1. But possibly singular, a rational curve, such that the Kx dot C is less than 0. Okay. And that's the first step. With this, so this thing here, this is something very special, Modi's bend and break technique. This one goes through, even if you start a variety, let's say over complex number. I mean, if you start with positive character, then that's excellent. But let's say over complex number or character 0 field, this one goes through reduction modulo prime characteristic technique. Prime characteristic. So the inside deal is that you basically take a affine chart or look at the equation of x, I guess, yeah, maybe globally will do it. And then consider the model of the variety over Z algebra, the coefficients. And then there, what you need to do is that sort of we have to increase this intersection number degree. So if kx is not NF, kx not NF immediately implies there exists at least one curve, let's call it different name, gamma in x, such that kx dot gamma is less than 0. That is for sure. You do not know a rational curve or anything. And then what the positive characteristic reduction model technique comes in handy is that you want to increase the intersection number to a very large number, high number, okay? And then the bend and break technique basically does this thing that that is the number, of course, controls the deformation of this curve in the Hilbert scheme, right? Okay. And then there's an estimation, right? What is the dimension of that point, the generic point of the locus in Hilbert scheme, and that part is sort of a simpler in terms of deformation theory which says that, okay, how do I say this? Okay, in a non-technical way, it says that sort of the way that is generally phrased as a slogan that if you have a family of curve that passes through a fixed point, by family of curve I mean from a home of P1 from a curve to some other to the variety. Okay, if that thing has a positive dimension and passes through a fixed point, all of the curves the image goes through a fixed point, and then that's called a bending. So it deforms bending. Then it breaks. That means one of the curve has to be now in that it has to be reducible with one of the component being rational, which passes through that fixed point. The technicality, but the ingenious part of Mori's idea was, so that deformation theoretic idea is known. It was known before Mori. That there's nothing new about that. The idea was that to produce something rational curve, you have to go through reduction mode technique, and to get this deformation theory to produce that thing. That was the ingenious idea there, Mori's idea. And once you have that, then he actually was able to prove something very nice structure theorem to the cone of curves. Yes, rational part is part of the deal. Yes. Correct. So if you not neb, it guarantees that there will be a rational curve. This cannot is not neb. That's part of it. That's the Mori's theorem. I mean, that's the starting of the Mori's theorem. Yeah, absolutely, yes. In particular, there is no reduction model. Sorry? Same proof works. I mean, there is sort of no. So yes, exactly. So you increase the degree by simply self-composing probabilities to have. Yeah. So in positive characteristics, there is same proof works. I wrote X for this. You increase the X minus C for yes. That was the sort of idea. Yeah. I mean, that is sort of, I think, still the only proof, exactly. Okay. I mean, there is some version for the analytic varieties. Kähler variety, yes. Exactly. So that is I'm making this point because I'm going to compare there that when you have a Kähler variety, Kähler manifold, there is no reduction mod P. Okay, so how do you overcome those things there? That's the whole reason of this background story. Highest negative value. Okay, let's see. No, not highest. I think, okay, so the bound is actually all the rational curves. No. Let's see. No, can you bound it? I mean, in the extremal way that you can bound that one of each of the generator, you can choose it in a way so that if this one happens, this is less than equal to twice the dimension. In case of smooth, it's just n+1 would work, but you can choose one from each of the extremal ways. And the other one, if you take some multiple of it, although that would be a possibly rational multiple, I'm not entirely sure what will happen there. Okay, so yeah, so right. Yes, exactly. Absolutely. So what happens is that, okay, so let me just statement here. Okay, like the full statement of Mori's theorem. So once he has that, then he can actually give a description, a very beautiful description of the Mori's theorem. this is the effective, all effective one cycle and take their closure in the classical topology inside of the n log of x. So you take the all effective one cycles, everything over R. So finite vector space, take the closure of that one. This one can be decomposed now as this. This kx greater than or equal to 0 plus countable number of this thing, this rays, these are called extremal rays, positive. Let's say I want to, okay. I is an I. What a good idea, let's just say, so I is an I and this I subset, it will be a finite also, potentially, this thing. And so yeah, this other graph has this property, and CIs are rational curves satisfying minus of k dot c. In this case, it is simply, of course, this is strictly greater than 0. Write it to everyone. 0 strictly less than minus of k dot c is then equal to n plus 1. For smooth n plus 1, no, singular is 2n. So yeah, CI. And this can be like drawn as a simple and nice picture. Is that, let's say, this is the Hakaplian kx equal to 0. This side is the kx positive, this side is the kx negative, and this is so yeah, this is the kx less than 0 side of the cone. This is the middle part. Okay. I basically, okay, so you don't think of these things coming out of the plane, I slice. So you're seeing it, looking at a face of this thing. That is correct. I do not know how to draw infinite one, but maybe I should do dot dot somewhere. It need not be finite. Okay, this could be actually counted to infinity, and you will simply have it if you, let's say, P2 will blow up at 10 general points. You will have infinity, and there is no positive part in that because everything is entirely taken. Okay, so this is this. Yeah. So and here's the thing. So yeah, once they have Modi's this, then Modi's the bend and break. Then Modi actually, okay, so Modi proved that each of this extremal ray can be contracted. Okay. And his proof was in dimension 3 only, and in a very explicit calculation, like sort of he contracted them locally, like analytically, and then glue them and look at that is actually projective maps. It was a very hand-on computation dimension 3, but then later on in the, I think in the 90s, at the beginning of the 90s, Kawamata and Sokurov, they gave a very nice, I mean, it was, I think, maybe originally due to Sokurov in dimension 3, and then Kawamata gave a proof in all dimensions using similar ideas, but much more simpler proof. Well, to keep track of the time, I started at 11:10. Okay, it's now 11:30. How long do I go? 40 minutes. So 40 minutes more. Okay. Okay, so that is 12:10. Okay, thank you. Now, not a Sokurov. Base point free theorem. So this one basically says that, okay, I don't know whether I should write the actual statement or should I just explain this thing. Okay, let me just explain into this thing. Okay, that if R, let's say R equal to, so maybe I should fine. This is a kx negative extremal ray of NEX bar, then there exists a contraction F from X to Y such that a curve C in X is contracted by F if and only if, let's say I switch in notation, let's say gamma in X contracted by F, if and only if the class of gamma, the numerical class of gamma is contained inside the extremal ray R, or in other words, is a positive multiple of the curve C. This is an if and only. Okay, this is precisely what we are contracting. Okay, so for example, a simple one, and by the way, this locus of all these curves, it can be the entire variety sometime, can be a divisor, can be something infinite dimensional, sometimes can even be a finite number of curves. For example, a simple one, let's say I take P1, P1 cross P1. This the cone of this one will simply have, let's call this one is X. The modicon of X is simply just everything is negative. There is nothing non-negative, and it's just well, sum of basically two rays. Let's call, I don't know how to call it, F1 probably, one of the fiber plus plus dot F2. And as you see, by the this contraction does not mean that Y is F is birational here. Okay, it can be lower dimensional contraction. So Modi's idea of doing a program a little bit different than the custom levels. That in custom levels, you always every morphism is a birational morphism. You end the final one is also birational. But in Modi's case, sure that those cases are already covered, because if there is a -1 curve in a surface, Kx is definitely not net, as you have seen. So it will do all the birational contractions. After that, there will be further more. For example, this one. This is a minimal surface already. Of course, the way the sense we know, but it's in Modi's minimal program, you will go one more step. You will contract one more of this thing and then go to lower dimension. And then you stop. As soon as you go to lower dimension, you say Modi program stops. Yeah. So here, if you contract this F1, you cannot singly just contract one curve. You contract the entire family. That means you will go from X to some this here. Of course, in this here specifically P. Yeah. So this is what it does. The alt statement, I have it in the slide because I have to compare. These are extremal, right? Both of them. Yeah, so because all of this is the class, every fiber is in the same class. Yeah, maybe. Yeah. Yeah, so yeah. So this is F1, all of them are in the class of it. Okay, so I'm going towards the. Okay, so let me just yeah, there's this one. Let me just quickly now tell you how it goes in a higher dimension, and then I'll go to my slides. To make more sense there. Okay, so in dimension, so arbitrary dimension is how you start. Basically, start X smooth projective, let's say. And let's just say stay over. I don't have to at least stay over. I think I should definitely stay over complex number now, because a lot of things are not known in positive characteristic. If Kx is yes. Yeah, so here I assume sort of X smooth, but the general condition is quite, the bar is quite low. For example, you just need to have KLT singularity, Kamatala singularity. For example, in particular, finite quotient singularity will do it, and this will be. If Kx, that is true, yes, yes. In positive characteristic, you still know it up to dimension 3. In high dimension, you do not know it, yes. Yeah, probably I should have said this thing, because even in this one, okay, sorry, yeah, thank you, I should correct myself here. Complex number, this is not known. Even for a smooth relative variety, the contraction theorem is not known in a high dimension other than 3. Positive characteristic, only up to 3 we want. the reason all of these things that is not known, this kind of things, that it really uses in a very strong way the Kawamata vanishing theorem and resolution singularity, both of which are the Kawamata vanishing simply fails and resolution singularity is not one or the other. Okay. If Kx is not an F, then there exists a contraction of Kx negative external way. This thing, okay? So let's just call the contraction F from X to, let's call it X prime. Okay. Now we have to sort of ask two questions from here, branches out initially. Hopefully I'm not going to mess this thing up. The dimension of X prime, let's say this is strictly smaller than dimension of X. If this happens, then we are happy. In this case, we sort of we basically say that we stop. We don't do anything. And these things are called then F from X to X prime. Let's write vertically. X to X prime is called a modifier space. I'll tell you that why you stop modifier space. So look at here, what we have here is that in this case, minus Kx, Kf is F ample. This relative means that anytime restrict to the fiber, it is always ample. Restriction to all of the fibers is ample. Relative Picard number is also 1. So that's very nice to have. Picard number of X minus Picard number of X prime, this is also 1. So that, and the general fibers are, okay, we have to do adjuncts a little bit, okay. Maybe not, let's see. Yeah, in this case, since I started smooth, general fibers are Fano varieties. Yeah, there's the determining characteristic modifier. The general fibers are Fano varieties, basically deformation of Fano varieties, modular of Fano varieties, and these things are heavily studied. Fano varieties is one of the heavily studied class of varieties. So these things are taken as a positive outcome, that we understand it quite well. And if the dimension of this thing becomes now equal, which one? Yeah, y is not necessarily smooth. By the way, yeah, X prime. So even if X is smooth, X prime is not necessarily smooth. Yeah, morphism is not smooth. No, morphism smooth would be no, almost never morphism smooth. X prime is not smooth. That is sort of a more sort of characteristic of MMP, that even if you start with, there are examples when you start with a smooth variety, no matter which contraction you do, it always end up with a singular variety. So that is possible. So that means you cannot expect X prime to be smooth, and that is sort of another hurdle in the MMP generally. Big hurdle. Okay, so yeah, so X prime not only not smooth, there could be a horrible singularity. Not smooth. So let me come to the other point here, that now this thing branches out here, that let's say dimension of X now equal to dimension of X prime. Okay, in this case, F is birational. Okay, and then there are two possibilities. One is the dimension of, so let's say codimension. Codimension of the exceptional locus of F is exactly 1, means it contracts divisor. Okay? I mean, at least one component is a divisor, then it can be shown that it is actually exactly one divisor exceptional locus in this case. Other possibility is that codimension of the exceptional locus of F is at least 2. In this case, what happens is that X prime in this case is necessarily singular. It's definitely singular. It can be shown that it's a singular, and the simple way is that the proof is actually almost tautological, that it has to be singular. Is that if it is not singular, so I have X to X prime, F, the exceptional locus of F is not a divisor, something greater than or equal to 0. Sorry, 4 dimension. If X is smooth, X prime is smooth, then Kx prime is Cartier, the canonical divisor, and I can simply pull it back. And actually, it's not even Q factorial, okay? And look at the difference between these two. The difference is that, I mean, should be a divisor, right? But there is no divisor in the exceptional locus. This divisor, this is supported, I can choose, okay, so if I should say, as we know, canonical divisor is not really that canonical. It's unique only up to rational equivalence, but I can always choose this K prime in a way so that this is pushed forward of it. Like first choose a canonical divisor on X, Beilinson push forward, it will be canonical on the X prime. Okay, I can choose it in a way, and then this one is supported on the exceptional locus, but there is no divisor. That means this must be equal. Now I had this thing that every time this contraction that I contracted something Kx is negative. That way, right? That side is supposed to be negative with the contraction, the fibers from this thing. So if gamma is a curve in X and that f of gamma is a point, then I'm supposed to have Kx dot gamma negative. And that's a problem. This thing is, well, yeah, supposed to be negative, but here I can see that this time gamma, this thing is actually 0. Okay. That means X prime is necessarily singular in this case. And this is a very, very big trouble. It's actually, in MMP, so we have to allow singularity, and there is a class of singularity called Q factorial. This one terms out that is not just Kx is not Cartier, it's not even Q Cartier. No multiple of Kx prime is Cartier, because some multiple of Kx prime is Cartier, you can take that multiple, pull it back. Let's say m times Kx prime is Cartier. Then pull back m times Kx minus m times Kx would have exactly the same problem. You run the same problem, okay? So not even Kx prime is Q Cartier. So this is a very big problem. And there, okay, I'm not going to go any more detail because, okay, yeah, I'm getting short on my time. Is that here, there's a big problem. There's something called this contraction here, if now is called F is a clipping contraction. And there exists a flip. Let me tell you at least simply what it is. So the idea is this one, that after you do the contraction, you want to replace X by this X prime. That's the idea. And keep repeating this process. That's the algorithm. Okay. So if it is smaller dimension, we stop. We say that we have at the end of the nodal program, we are happy. If it is codimension 1, we can actually, if it is exceptional locus codimension 1, then we can replace X by X prime and ask whether Kx prime is F or not. It will make sense. Okay. The Kx prime will be Q Cartier. If it is this one, we cannot. Okay. And this is sort of a okay, maybe just draw the picture instead of saying anything. See, if it's this one, the codimension is greater than or equal to 2, there's this beautiful idea by Miles Reed. He came up with this thing that something looks like very topological, but it has to be done in algebraic way. So let's say I have it from X to this is X prime, this is our original F. And then, so yeah, let's draw the picture. All right. So let's say something, it's an abstract picture. Is something, I'm thinking of this as a three-dimensional thing, object at least. So these are curves, C1, C2, C3. So if it is X is dimension 3, then the exceptional locus, and then there's a codimension of the exceptional locus of F is, well, even greater than or equal to 2, that means it's simply that exceptional locus is union of curves, right? Finite many curves and finite many curves, exactly. So let's say these are this thing, and this is the, let's say, our F. So this comes to this point P1, P2, P3. So, and this I have this thing that Kx dot these Ci's are strictly less than 0. Those are the only contracted. Okay. And we lost the smoothness here. This is X prime. Not just smoothness, we simply have that Kx prime is not, let's just say they use the technical term of Q Cartier. Means that no multiple of this thing will be Cartier. So I cannot replace X by X prime and ask the same question whether the Kx prime is an F or not. Okay. So my city says that, okay, when you have this thing, can you produce something, let's call it X plus, okay, such that this one happens, C1 plus, C2 plus, C3 plus. This is called F plus. F plus is also a birational morphism. Okay. There is a natural induced map such that this is now a rational map, a birational map. We prefer that in this side I will have this picture that I don't have to write here is that Kx plus this variety. So this is the accessory locus of this morphism A plus, such that with the C1 plus, now I should have a positive indices. So means I flipped the curve because I had negative. So idea of the minimal program is to remove the Kx negative curves. Whenever Kx is not enough, remove those curves. Okay. So here I did remove them, but I ended up with something that is very, very singular. Okay, I cannot continue the program. Okay. So we said, okay, replace this one with something better that has this thing that okay, that you replace the negative curve with the positive intersection curve. So the canonical this thing here, Kx plus is F plus ample. And remember here it was Kx minus Kx is F ample in this case. Sort of flipping, okay? Negative curve to positive curve. And we wanted that. We wanted to make as many curves as possible has positive intersection with the canonical. Okay. And turns out that it can be done algebraically, but the proof is, of course, very big thing. Modi proved this thing in dimension 3, 1925. That was his big theorem. Existence of flip. So this is called flip. This X plus is called flip. Okay. This thing. And yeah, and the big, very big theorem is this BCHM, Baker, Cassini, Hicken, McConnell, that in 2006 that flip exists in all dimensions. The existing over complex number flip exists in all dimensions. Yeah. So and correct. It's a surgery. Yes. It's like a surgery, but that's exactly that's how Modi did it in dimension 3. See, he did it locally, analytically, and then when he glued, it turns out that's actually projective variety. Okay, this is because of the relatively positive morphism, he can glue it turns out to projective variety. But in higher dimension, that is actually very different. The proof. This X plus there is a so Morris Masrid gave this idea that he should do this thing, and he actually told them. I mean, he gives them the. If I assume this property that characterizes X plus, how it should come from X, and this is what the X plus is. That the X plus, if it exists, then it should be this proj of this thing that F rho star of okay, so I have to do m greater than or equal to 0 of this OX m times X. No, this is a sheaf. This is a sheaf. So yeah, no, H not would be a global. It's not the global. It's the local one. I want to clear the entire morphism X plus to F. So this is a natural projection from this to the F prime. We call it F plus. Okay. So that means this X plus the flip will exist if and only if that sheaf of algebra is finitely generated. Okay. And that is the big theorem of this is not how Modi did it, by the way. Okay. This is Modi's idea was Modi's proof was very like local, like so saying. So this is the big theorem in 2006 by originally due to Christopher Hicken and James McConnell. But yeah, this ring is finitely generated. Okay, so therefore flip exists in all areas. That's a very long and complicated. Yes. Yeah. Exactly. Yeah, that's the issue. So that is why in higher dimension they cannot. That local like a construction and patching the two that you cannot claim the now is a bright projective right. That's definitely a problem. So no, they did not know that. They did not. I mean, in BCHM introduction, they talks about it quite detail that you can always do copy pasting. That will end up being algebraic space. You cannot claim that that's a projective right. So in the existence of ample divisor would be very difficult. So this is the global approach. It's sort of a magic that when the once it came out with this idea, I mean, just from the formal property that you want on this one, it characterizes that it has to be this if and only. Okay? The flip exists if and only if that ring is finite. That's right. That's sort of the perfect connection that you need. Okay, so I think this is the preliminary. It is longer than what I wanted to do, but okay, this sort of gives the idea. Yeah, so once you have that, so let me just tell you one last thing here. Once you've had that, you replace X by not X prime, but X plus. Okay. Only problem here is that see, in this contraction, the relative Picard number of X over X prime was 1. Here, unfortunately, also the Picard number is x plus over x prime. I mean, not unfortunately, I would say 1, which means the Picard number of x and x plus remain the same. This is a big problem because when you do this kind of contraction, divisible contraction, here Picard number drops exactly by 1. Here also it drops when then you put it back. Okay. Then that leads to that you do not know whether this process will terminate after a final step or not. That's called the termination conjecture. That is known in dimension 3, many cases in dimension 4, but other than that, it's not known unless the variety is general type. In general type case, the BCH and again they prove that at least certain type of contraction is happening. Termination is happening. Okay. That's the sort of the very long introduction, I guess. Not a quick introduction. Okay, so yeah, so here's the thing. Basically, I said the story. In 1980s, yeah, Modi basically started this thing, and then a lot of people contributed, and again, Modi basically finished it in dimension 3 in 80s, and the next major breakthrough is due to Dirichlet and Hagen-Mackernin. And then the obvious question is, there are two obvious questions, of course, in a positive characteristic and for Kähler manifold. Can you do these things? So there wasn't much of an interest in Kähler manifold because of the obvious issues. This thing, the Modi's bend and break will not work. I mean, I shouldn't say fail. I don't know how to phrase it, but it doesn't make sense. I mean, okay, the statement makes sense, but you cannot do it. Reduction of P is not available. There's no meaning to that. So there's that there. Another is that the base one free theorem. Okay, so this is the sort of the, I would say, the core of the problem, because as it turns out, that is not so important in Kähler manifold to do that. However, the contraction theorem I told you comes from base one free. This is very important. Okay, here's the thing statement here that I did not write there. This is the statement you said that X is smooth relative right, it is a NF Cartier divisor. If AD minus K is NF and big, then some high multiple of this is semi-ample, meaning this gives a contraction X to Y. And it actually contracts so that M times D is pulled back of some ample divisor. And here what happens is that this D intersects those curves in the extremely precisely with zero intersection number. Those are the only curves that is intersects with 0. And so this is the thing that gives us the contraction that I wrote down here. And the problem here is that when you have Kähler manifold, which is not necessarily projective, the hypothesis that is the difference is big is not satisfied. On a Kähler manifold, if you compare Kähler manifold, if there is a big divisor, it automatically becomes projective due to Mohali's theorem. Okay, it's immediately spread. So that's the failure. So in dimension 3, yeah. So that is sort of a first problem. There is a several layer of problems. The other problem is that in a Kähler manifold, the Modi cone, that is sort of the bread and butter of the MMP, can be very, very small. There are compact Kähler manifold which has no positive dimensional intermediate subvarieties, even the singular one. Okay, you can take a simple torus, means take a torus with a sort of a general, the lattice basis. Okay, and then you can sort of create a condition where there is no intermediate dimensional subvarieties of it. So that means this could be actually completely empty, this NX, okay, instead of that. So what do you do? And so that means it's not, or maybe, yeah, very few. So it doesn't really reflect the geometry of that thing. And so what Campana and Pirandal and Holding, they did it in, okay, so this is not the definition, reference for the dimension 3, that you have to enlarge this. These are not the right class. The Modi cone is not the right thing to look at it for Kähler manifold, as well as the n lower one even, okay, the n upper one, for example, the Picard group, okay. Picard group also has problem because, well, Picard group supposed to be, is dual to the, not Picard group, the Picard n upper on X. N upper on X will similarly have not enough function in it because that is dual to n lower on of X. If n lower on of X is not there is only finite limit, then n upper will not have it. We'll have a problem again. So these are all problematic things. So this is what they came up with. There are normal compact analytic variety. We will consider now Bort-Chern cohomology. Okay, so this is simply that you take D close to 1 on form. Okay, so I do not want to say what is local potential. I just forget about that at the moment. Local potential is locally dd bar of some smooth functions or whatever that is needed there. Okay, D close to 1 on form modulo that's globally exact. That one forms is a Bort-Chern cohomology. So the good thing is that when X is a compact Kähler manifold, this H1 or this is exactly what you want. You can interpret it as a D bar cohomology, Dolbeck cohomology, whatever you want. So that's coincides. So So this entire thing is taken as a now a replacement of n upper on of x. I hopefully wrote that thing in the next slide. No, I didn't. Yeah, this is there, is the right. So we take this one, the Néron-Severi, as the entire Botchan cohomology. Okay, and it is actually larger than the Mori. I'll just say it in a few slides. That is actually larger than the Néron-Severi vector space, even when x is projective. Some cases, in that case, it can. And for the n lower one of x, we do this thing that we need it to be a dual to the n upper one. So we take currents. So currents are basically differential forms with distribution as their coefficient. Okay, it's something comes from analysis, and then they sort of acts on differential forms of complementary degree. The interesting part is that if we take, let's say, curve, if you integrate one form on it, okay, complex curve one form on it, that is always a current of bidimensional one current. So all the curves that we take, that like let's say x is a projective variety, not just an analytic but projective variety, then the n lower one of x, or this one is definitely going to contain our n lower of x that we know, which is only the curves first. Yes, that can be proved. Yes, because if first prove the Botchan cohomology, you need certain thing. For example, I think to see it easier way is that if you, I think it's always finite dimensional, but the simpler case would be if x has rational singularity, then the Botchan cohomology embeds inside of H2 of x comma r, the Durham cohomology. Okay, I'm sure that one. Yes, you can. Oh, yes, absolutely. There you go. Yes, yes. You resolve singularity, go there. Yes, yeah. Real singularity exists for that one. Okay, and there you have. Yes, thanks. That works. Yeah. Yeah. So it's always finite. So then it turns out that these things are this n upper and lowering these general settings is also a natural pairing, perfect pairing. And then again, in this compact Kähler manifold case, n lower is exactly h n minus one of this. That is explained. The Poincare duality gives you exactly that. Okay. And here's the interesting part. This thing, the Néron-Severi inside of this thing, okay, it can actually be strict even when x is projective. Okay, so you can have, for example, this thing, the smooth projective K3 surface. Then H1 on the Hodge number is always 20, but there are plenty of examples, class of things which Picard number is less than. Yes, there's exactly. You have real one-on class which is not rational. If it is rational, then it will come from line bundle and everything is fine. Real one class that is not rational. So basically, we just look coefficient. Okay, so so now, so we have n upper and n lower. We need the generalization of the Mori cone now. This is the generalization that now we just not take the curves. I mean, curve of integration of a curve is definitely going to give you the thing that we want. That is sort of the type of thing we want. But we take also to be the positive closed current. Okay. So basically, it's a current of bidimensional one. I think I have written before that thing. So not just the like if I take any curve, the current of integration of this thing is always a close positive current of bidimensional one. We collect all of this close positive current bidimensional one instead of n lower of x. Okay. So this is something more. This not all of these things are represented by curves. Okay. Something more. And then in a sense, this is actually continued that. Again, this dimension could be strictly larger. The same example works because they're n upper one, n lower one are the same for surface, right? The same example of this dimension could be strictly, this could be, inclusion could be strict. Okay. I'm getting close. So let's move on. So let me just quickly define what I mean by, I have to define what is a singular Kähler right? Because MMP leads to singularity. And this is sort of, okay, if you haven't seen it before, this may feel a little bit uncomfortable that a singular Kähler variety means there has to be a Kähler form, and on a singular variety, a Kähler form means you actually take a Kähler form on a smooth part only, okay, first. And then you see that when I take a singular point, and then that singular point, because it's analytic variety, has always a neighborhood which embeds into some open subset of Cn there. And then you say that, okay, and then on that V, there should be a Kähler form coming from the Cn or just to V, doesn't matter, such that omega intersector with U on the smooth part intersection this should be same. So some compatibility that you can always locally do this. This is a definition by I think originally Griffith, and then Riemann formalized all of these things that you can do this sort of things, all the punctuality holds. You can pull back this kind of, you can define, doesn't have to be a Kähler form. You can define a forms on a PQ form on a singular space, and then it satisfies the usual punctual property that if you have a mopsum between two things, you can pull it back and those things will hold. Then we define a nef class. A class is called a nef class. If it can be sort of represented by nef class, and then if this is the class is called nef, if you can sort of, this is, you're moving it in the within the cohomological. This is a smooth function. Okay. So think of this thing that I have a divisor, alpha is a divisor D, and I will call it a nef. If I can move it by a rational function, like divisor of a rational function f, such that that is greater than equal to minus of some ample divisor. Always think of Kähler form as ample divisor. It has a similar property, intersection property. Okay, ample divisor intersect every subvariety positively. So does Kähler form. By intersection, I mean the integration of the. Okay? So this is the thing. Okay, nef. So you know this thing. This side is still nef plus ample is ample, right? So that's the time we are trying to mimic here. And similarly, so using this is the nef class, we can define a Kähler cone and the nef cone. Kähler cone is the open convex cone generated by the classes of Kähler forms. And the nef cone is this kind of nef classes, and it turns out perfectly that they are exactly what happens in the projective case. The nef is the closure of the Kähler. Yeah. Yeah. Sorry, I didn't ask you, what do you mean by that? Yes, definitely it has. This nef cone will, this thing will span the entire H11 Botchan cohomology. Yes, all of these things are the whole. Kähler gets to another one, right? Yeah. Okay, so yeah, and then also this thing that the Modi cones will be dual to the nef cone. Those properties also hold all of these things. And then and also this other interesting property that the Clement-Modi criteria that the divisor is ample if and only intersection with every positive, every non-zero class in the Modi cone is positive. Okay, so that also holds here. Okay, so maybe I should now just okay, keep giving interesting example, putting example here, but I don't have much time now. So just a quick thing that we define a nef in a different way. So if you start with a, let's say on a compact Kähler manifold, I take a line bundle. I can choose a connection, some arbitrary connection, go to create its Chern class, right? Okay, and look at its cohomology class inside of the H2. So nef in the sense that we just define analytic sense is actually more general than the nef in the sense that algebraic sense that we do. Okay, it can happen that if you that if something is algebraically nef means intersection with every curve is nef, but it's actually not analytically nef. Not in a projective variety though. You need a if you have something else smooth plane. Sorry.
Guess we can summarize. Actually, real solution Zoom aspect.
Not getting the question, which you put, but tell me. Okay. Okay, so this is not going to happen in a projective variety, of course. Okay, if it is, if there are surfaces which are algebraic dimension is equal 1, means that their set of the field of monomorphic functions in the algebraic case that we call the field of rational functions, that is not same as the dimension of x, strictly smaller than x. Then you can have there is a vibration. There's this kind of example. If you look at the classification of compact complex surface, that book. Yeah. Yes. But I thought, that's what I absolutely yes. But I think that is sort of a abstract, is sort of maybe a little bit more like easy to confuse that, because now I have a vibration and all the curves on x are fibers of x, right? So on the base curve, I can simply take a point. A base curve is always a projective curve. The complete compact curve is always projective. So then I can take a point, and minus of that point is of course anti-ample, because a point is a ample divisor, and pull it back. Pull back is d, that is anti-effective, so it cannot possibly be nef. Okay, because with Kähler class it will have negative intersection now. Okay? However, this is nef in the sense of curve, because all the curves on x are fibers, so that is always G. Okay. So these kind of things happen. So in the Kähler category, we work with the analytic Kähler, analytic nef definition, not the algebraic one. And then obvious question is that how we do the rank MMP. Turns out that now have to sort of do it faster. Okay, that when you just involve the line bundle is the canonical line bundle, then it does transform that algebraically nap means intersected with curve and the analytic sense that these two are set for the canonical parts. And there's a proof about using a generalized version of Zariski decomposition, okay, with Zariski decomposition called Boxon decomposition. Let's not get into that. I don't have time for that. And so that is sort of the beginning that, okay, if the Kx is not nap, then, I mean, Kx can be, whether it's nap or not, can be tested using just necessary for curves. On dimension 3, that was originally by putting Paternal. And then, okay, sorry, I don't need this one. Okay, and here is the thing that, okay, now, yeah, so now how do you produce rational curves on X? When Kx is not nap, so it's not good for me to say this thing. Yes, okay, so here's the sort of a sketch of the idea that when Kx is not nap, then I know now that there is a Kx negative curve, not necessarily rational curve. Then you basically consider whether it's very rigid or not. Does it deform or not? Okay. And since just the fact that X is dimension 3 and we work with terminal singulator, maybe just simply take smooth variety. Okay. You can use deformation theory to analyze that in each cases. I mean, it has to be that there is a rational curve. Okay. In the class of this. So I'm choosing this C from basically one of the extremal rays. Okay. In a sense, although I haven't defined it, I haven't proved the form theorem yet, but sort of we start analyzing this thing that if this happens, then there is a rational curve. So the problem, all these things there is that they reduce the problem to basically surface, and then there you apply Beilinson-Bernstein in surface. And so yeah, so this is deformation theory, and that is sort of the drawback of the construction, that the proof of everything that they Horian and Paternal did. So they prove this kind of form theorem then, okay, for this one. There will be counter limit rational exactly with the similar property using deformation theory in these things. And yeah, so that is sort of the, so let me just go back quickly, okay, that so all of they did everything dimension 3 for terminal singularity, and that probably with that thing, their proof is very much dependent on deformation theory. That means we cannot deformation of curves on 3-4 particularly, and that is extremely convenient because if you look at the deformation dimension of the Chza variety at a point, that comes with the minus of Kx dot C plus n minus 3 into times the Euler characteristic of the curve, which is amazing that for dimension 3, that part is 0 because n equal to 3, okay? In high dimension, this is completely useless, that formula, okay? So it's a sort of a very lucky coincidence that it works in dimension 3. So that is where I and Christopher, we started working on this thing, that from their paper, that how to do this thing in higher dimension. So the problem is always that whether we can contract something. Let's say we have even extremal, can we contract? Because the basement free theorem is completely unavailable. So this was sort of, so this is sort of a very classical theorem of Fujiki that sort of tells you how to contract thing in analytic variety. It's a very sort of hands-on thing. So you want to contract something from X, so you have to know what you want to contract, which is S in this case always has to be divisor, and where the contracted thing will go. Okay, they need to know the target of the contracted thing as well, which is sort of seems impossible in the way that we do it for NLP. And then it says that you can construct a Y around that T then, okay, such that this thing X to Y is actually a birational morphism and the extension locus of G is exactly S. Okay, it's a very local construction and going this yeah, very complicated one for sure. Sorry, the true solve. Yes, yes, it's exactly that. Yeah, and then yeah, so this is sort of our idea that we try to do this thing, and it will be sort of a very convenient version of this one. That is, this sort of we now go back to the Sokurov idea that in higher dimension to do MMP, we need to consider something called PL type of pair, PL divisor contraction, and this thing here we have to consider the log category. Now the variety with the divisor, and this S plus B, this is a Q divisor, so that the coefficient of B are strictly between 0 and 1, and the S has coefficient exactly 1. And then you sort of do adjunction of this one and do induction of dimension. So that if I know contraction in lower dimension, in our case I know in 3 because, well, it's been done by them and also us, okay? Then I can, if this kind of contraction I can extend. I know that what is the target space because on S I will know the contraction by induction step, and then I can extend, I can construct the Z using the physics theorem. So that is sort of our main idea. And then, yeah, okay, sort of. already past 2 minutes past time. So this is the sort of the detail that how we use that theorem to prove things. So let's not go into any of that. Let me just tell you finally what we know so far. So we definitely know the most general case for dimension 3. They did it only terminal case. We did it all the remaining cases. Christopher, myself, and also another Wenhao with him. And we also know Kohn theorem. There's something called analytic base point free theorem. There's another version of that. We know that one as well. And then we know some higher dimension. We proved some higher dimension result as well, that when x is dimension 4, and then the canonical has, let's say that, some section. Then Ithaca dimension of the canonical, the dimension is non-zero. Okay, greater than or equal to 0. Then we also know how to produce mineral model. Okay, and also that if you take a projective morphism between analytic varieties, relative MMP, but for positive morphism between analytic varieties now. Okay, then also we know how to prove. This is the entire, this sort of the exact result that the BCHM proves for projective varieties. Okay? So we have exactly that thing. We also have proved the existence of flip for analytic case in all dimensions. This is sort of nonsense. Thank you.
Any questions or comments?
Pseudo thing for well, let's see, not pseudo effective. I mean, we can always create very silly examples that you sort of the torus and maybe you blow up 100 points of torus, which are not less level and variety, these sort of things. So the goal of this program for Kähler variety is actually not similar to that of projective variety, that we are not going to do moduli of things at the end of the day. Right? This is this one of the idea for this thing is that Kähler-Ricci flow. The people who do Kähler-Ricci flow, for example, Tian and Song, they have a conjecture called analytic. There is a program, they have analytic neural model program. Okay? So they basically show that if you start with the Kähler-Ricci flow and you run, the flow has a solution up to finite time, let's say. When it achieves a singularity, at that point, the threshold of the singularity, that value of the t is precisely the Neff threshold that you get here, which gives us the contraction. So that contraction is exactly contraction. So if I take a projective variety, and I take the Kähler in the Kähler-Ricci flow, the Kähler class to be a first channel class of the ample divisor coming from that. Then when they reach the singularity, the contraction is precisely our contraction of the movement. So there is a very close relation, and there is a lot of conditions related to it. So you sort of need to have a better MMP development for analytic varieties to deal with those kind of things. So that is sort of one of the, not anytime soon, very, very far future goal, but to try to do something about that. But at the moment, there is a lot of development to be done with that.
If there are no other questions, let's thank the speaker again. It's a great pleasure to have Professor A.J. Parmeshwaran here. He's from Kerala School of Mathematics and formerly from Tata Institute. The title of his talk is on the stratified fundamental group.
Yeah, thanks for the organizers to invite for the invitation. And I always start with one sentence, especially want to say about Kapil and Nitin. And they were really our kind of mentors or kind of, I don't know what should we say. In my second year, I was lecturing. In fact, they pulled me and said that you should give lectures. And so I said, I'll give something in characteristic classes. I started lecturing from Milner. I looked at the book, goes there, and then totally prepared. I started writing down the cell decomposition for Grassmannian. Started writing down the coordinates and said that this is a disk. These people just stopped me. Said it's cell. I said, yes, it is cell. He said, no, it's affine cell. And it took a much longer time for me to realize what it means. That was kind of the beginning, and I couldn't go any further from there. The lectures more or less stopped. So that was a kind of training we got from TIFR. Yeah, the difference from cell to a fine cell. I was beginning as purely in topology sense, and took much longer to get into the algebraic geometry and understand the real differences. Okay, with that, I'll begin my topic. So today I want to talk about this étale fundamental group and stratified fundamental group. So I think we already saw what is an étale fundamental group. So X smooth projective, and we are looking at general X and Y. Smooth projective, X to Y and finite separable map. It's okay, or shall I write it bigger? Okay. Now, so there is a natural map from phi1 étale X to phi1 étale Y. Okay. So here, as we saw earlier, it's been looked up as all étale covers of X, essentially defined by étale covers of X. The pi1 is really defined by étale Galois covers and take their inverses. But for me, I wanted to look at very differently. Actually, the way that we look at from many of these purposes is there are certain kind of vector bundles which actually form a Tanaka category whose dual is this. So both these words, Tanaka category and the covers and so on, will be vanished, and we'll practically work with vector bundles. That's really the idea. So this corresponds to, which means there are vector bundles which becomes trivial on an étale cover. And this side also same thing. And there is a map given by a V mapping to F upper star V. So the point is, this collection, it forms what is called a Tanaka category. So I'll just, and essentially they are being vector bundles. I'll say some 2 words about Tanaka categories. I give a few examples. And then I will introduce what is stratified fundamental group. Okay. So how do I get back this one? So Tanaka category. Not really the full definition, just a working definition. X to Y, phi1 X to Y will Y. Oh, vector bundles is in the other way, sorry. Now from Y to, pullback is from Y to X. Yeah. Yeah, anyway, it is this map, but it goes from this to this. Yeah. Direction is a bundle from Y is pulled up to bundles on X. So this Tanaka category is supposed to be the category of the representations of the group. So the duality works like that. So given a representation of a group, if I have a group map, the representations of the image group going to give the map the representations of the original group. That is why the map goes, in the category level, it goes from here to here. Okay, so the working definition of Tanaka categories, you really take inside vectors. You consider a, and the collection of vector bundles satisfy one condition that really need to be checked is its abelian. That means given V to W, phi, kernel phi and co-kernel phi should belong to tau. Given V and W in tau, and take any map, any morphism, that is just a sheaf homomorphism between vector bundles. really says the kernel and co-kernel should also be vector bundles. So that's what it means that the collection tau is abelian category. And the other condition that I need is its tensor category. VW into V tensor W is in tau. And then there is a third condition I should check is O is in tau. Pardon? No, I take full morphisms. If I take a semi-stable bundle of degree 0, any morphism, kernel and co-kernel, on a curve. Higher dimension, one has to be a bit careful. Yeah, projective, yeah. You need a fiber functor? Yes. That's already there. The whole point is many of the things are already there in vectors. So x in x, if x and x in x, then you can send V to V sub x. This fiber functor is already, that is the one advantage of working with the inside the vector bundle. So there are many things I don't really need to, they're all inbuilt here, except A and B are the most important things to be checked. And often not even B, it is really the A. Okay. So now examples. Of course, first one, as we said, étale trivial bundles. B, there is another essentially finite bundles. They are sort of these étale trivial bundles. One can prove that there is a finite polynomial which satisfies that. And you might first take all bundles which satisfies some two distinct polynomials. Okay. So this means there exists f not equal to g in both in Zt such that Fv is isomorphic to Zt. And yeah. Sure. Okay. So look at all those bundles, and then you take the Tanaka category generated by that. Take all homes and take the kernels, co-kernels, you include all of them. And they are called essentially finite bundles. They also form a Tanaka category. And that's a category defined by Nori. And he said, that's the right kind of fundamental group one should look at in characteristic P. Because in characteristic 0, every morphism is automatically separable. So if I take a Galois, I get a group covering. And in characteristic P, you need to replace the group by a group scheme. So this essentially tells you that you actually have a finite group scheme cover. When I move into Tanaka category, the corresponding dual is a finite group scheme. And then C is bundles with all Chern class vanishing. Okay. So this category is called category with flat connections, and essentially looked at by Simpson. Probably the first one who looked at that, and it's so the corresponding group scheme we call it Pi1S. Okay, and then the D is homology. I think homology should be enough. I think. Okay, yeah, I think homology should be enough. Torsion bundle anyway won't come. They are all very good bundles. So, but anyway, they are actually genuinely bundles on everywhere. So they are not torsion bundles. Yeah. Yeah. And the other one is bundles which have grading by semi-stable or actually stable. Grading by bundles of degree 0. Okay. This is even a bigger class. So the point is, even if I take a semi-stable bundle and try to look at order Riemann or the kind of the corresponding by the Sokal filtration or something, what may happen is that the sum could be a bundle, but the quotient will not be a bundle. That is a very standard example. So that is why set of all semi-stable bundles of degree 0 is not a Tanaka category. But if you take this, this becomes a Tanaka category. Or again bundles, yeah. Are stable of degree 0. Yeah, this is like kind of a Jordan holder for the given bundle. Yeah. So the first one is called, so the names are like, this is pi1 et al. And this is pi1 Nori. And this is pi1 kind of Simpson. And the last one, we normally call it just LF graded bundles. And then, of course, the very last one I want to, what is it? Oh, it's locally free graded. Yeah. And the last one is stratified bundles. So this means, so this is in characteristic 0. This means bundles which has flat connections. Okay. While in characteristic P, the problem is just flat connection, there is some issue. So it's been, there is a theorem of Nicholas says that when you have a P curvature 0, a connection with a P curvature 0, then it descends. So the flatness should be thought of as kind of all order P curvatures are 0 in some sense. So in other words, it should be something that it should infinitely descend under Frobenius. Yeah. Yeah, this condition was for Frobenius. So this means, so this is how we are, right now I'm just writing it for the characteristic P. So this means a collection of En such that En plus 1 En is equal to F upper star of En plus 1. So that means the En plus 1 is a descent of En. The En plus 1 pull back to En. So for that E, call it pi1 strat of X. And then it can be seen if you have got an et al. Trivial bundle, then you can actually construct a descent. Okay. In fact, if it is stable, the descent is more or less constant. So up to some this thing. That means pullback of a stable bundle and a finite pullback of bundle, power of Frobenius, it gets fixed. Quite true for semi-stable, but the descending theorem is true. It just keeps descending. So that gives you a map of inclusion of A inside. So that really gives you A is inside E. And there's also inside B, inside C, and inside D. So that produces morphisms. And in fact, all these are faithfully flat inclusions in the categorical sense. And hence, the induced map on the groups are actually surjective. So there are surjective maps from here. Okay. But this is some very different kind of looking, sort of an independent look. So the point here, now the theorem is, so in that context with X, Y, smooth projective, smooth projective varieties, f from x to y, finite separable map. Then with phi1 eta x, call it f lower star, an isomorphism. In fact, this also can be shown easily. Then f lower star on phi1 stratified x to phi1 stratified y is an isomorphism. Surjective. If I assume only surjective, then I get surjectivity. And if I also assume isomorphism, I'll get isomorphism. So this is the theorem. So this is joint with Indranil Bishwas and Manish Kumar. So now, let us see what is the idea. The idea, as I said, we don't really look at groups as groups, but as a corresponding Tanaka categories. So what I'm having is, given an isomorphism of all the étale trivial bundles, I would like to say all stratified bundles are also isomorphic. So there is clearly a morphism. So there is a surjective morphism from here to here and there. On the other hand, if this is an isomorphism, this will also become an isomorphism. So this theorem is already known when so not as a relative version, as an absolute version was actually proved when the pi1 is trivial by Eno and Mehta, and it was actually conjectured by Giesecker. So it was a Giesecker's conjecture that on a simply connected variety, there are no stratified bundles. And this theorem was proved by Eno Mehta in 2010 or something. And later, one relative version is that if pi1 et al. Pi1 et al. X to pi1 et al. Y induces zero map, suppose that becomes trivial, then the stratified level also, it is trivial, is proved for any morphism of two varieties by Srinivas and Eno. But here we are asking for more. So trivial probably is somewhat easy to say that something is absent, it's not there and so on. While here we have to recover all the bundles. So we do need conditions on the varieties. So that's where we put two conditions and the map is that it should be a separable map and finite. Okay. These two conditions are required for us to recover the bundles to give the isomorphism. So when you don't put any conditions and ask the pi1 map is trivial, then stratified pi1 map is trivial is known by Srinivas and Eno in I think it's 2019 paper. Yeah, 19, not 90. Yeah. Okay, so let me just give some rough sketch of what goes in the proof. See, first of all, what we have is a bunch of bundles, okay? A sequence of bundles. So, and what I know, the given the conditions are all about some étale trivial bundles. So, given a bunch of bundles somewhere, so in the moduli or something, and given some finite bundles, some condition that is given. How do I interplay? So this is a theorem for FP bar. For FP bar, so take for K equal to FP bar, then the theorem of Harish-Chandra. Let's take that theorem. Let N be a variety defined over FP bar and P from N is dominant rational map. Then the set of points P power n z equal to z as n varies is a dense subset of n. So if you have a dominant self map in characteristic P, that too over FP bar, then the set of torsion points are dense. So this is what we'll be using. So essentially what we'll be doing this n as take this bunch of bundles, if it is infinite, take that orbit. So there are infinitely many points and take the Zariski closure. The n will be that. And then on that, what we will realize is there are lots of torsion points. So now I wanted to state a theorem of Lange-Stuhler. Says what are torsion points for the Frobenius, and the phi will be taken to be the Frobenius, because these are all under the Frobenius images. So if I take this sequence and look at the Frobenius map, okay, what is called in those spaces, it's called the Verschubung. So when you look at the Verschubung map, it's clearly dominant because all these are there. So it's an infinite set. If it is infinite, if it is finite, of course, it's already torsion. We'll get it from the theorem that I'm stating. Yeah, appropriate. Yeah, usually moduli space, sometimes more. Yeah, sometimes for finer moduli. So we will come to that in appropriate spaces right now. I'm just giving a rough idea about where to look for and what is really the relation between some this infinite set and suddenly you've got some finite thing, and how do you connect in terms of bundles. Okay. So this is theorem of Harish-Chandra. Then the next theorem. Lange-Stuhler. ST Euler. Oh, Harish-Chandra. HRU. Yeah, sorry. Harish-Chandra. Yeah. And in fact, this proof, the original one, I think is still not published as far as I know. And he also didn't bother to do it in that fashion. And it's a proof based on model theory. But on the other hand, later Warshawski and I think maybe something from Delhi also I heard, I don't know. But Warshawski, I certainly have seen it also, has given a algebraic geometric proof of this. So oh, okay. Yeah, about the Langevin estimates. Right? Yeah, right. Yeah, but we just needed, we essentially need only this. Yeah, right. Let V be a vector bundle. Smooth projective variety. I'm not sure whether this condition is real. I think so. And Suppose there exists n such that fx n upper star of V is isomorphic to V. Then V is et al. Trivial. So the F torsion points, F torsion bundles are precisely the finite bundle. So combining these two are the main tools to compare from et al. Fundamental group to. So the point is, when you have a stratified bundle, then you put all of them, realize all of them in a moduli space. So for instance, if they are stable bundles, so one thing you can prove, any stratified bundle, beyond certain levels, they have to be semi-stable. Okay? Because any Harish-Chandra, because you go down, and then En is actually pulled up from sufficiently small descent. So the Harish-Chandra, if there are length here, it will go up to P times length. And that P power R, or whatever the difference. So that becomes larger and larger. So it cannot happen that all the descents are unstable. Similarly, they also have to have all Chern classes vanishing. Because Chern classes also, when you pull back, it becomes P power n times some other Chern class. So this is a fixed bundle. It's coming P power R of something, some other bundle. So some numbers and P power n. So it cannot be P power n for all kinds of numbers because they are actually integral. They are not divisible. Okay, yeah, right. Yeah, here we'll need only that. Yeah. So with that, so you need a moduli space where all these kind of semi-stable bundles or stable bundles. First, so the original proof was first they do the stable bundles and prove that. So if there was so for instance, suppose you are a simply connected variety. Suppose there had a stratified bundle. So then you take, suppose there is only finitely many. Then by this theorem, it says there is a et al. Trivial bundle. But et al. Trivial bundles are trivial for simply connected varieties. That means V was trivial. Okay. And if there is infinitely many, then on that moduli, you take the orbit and look at the first Shubham, the phi to be the phi map to be the first Shubham. Then one knows that there is kind of a dense set of et al. Trivial bundles. But et al. Trivial bundles are trivial. That means n must be a point. But on the other hand, it is a positive dimensional variety. So our assumption that the existence itself was wrong. But then one has to argue a little more about getting the extensions. So in around 2019 itself, there was a nice paper of Sun. Actually, he produced, what he did is he simultaneously produced all semi-stable bundles in a fine moduli. So this moduli, so that is where we will look into. So this moduli, first in characteristic 0 was constructed by Simpson, called representation spaces. What you do is take a bundle and fix a point and fix a frame over that point. So that means fix a trivialization of the fiber and then fix the polynomial, Hilbert polynomial of that bundle. With this triple, so the theorem of so the third main ingredient is this theorem. Also 2019, I think there's a paper in Advances. He proved that the representation representation spaces like R, X, a point small x, and a polynomial. Let's call it psi. Is it? Fine model. So using this, what one can say is that whenever you have a stratified bundle, and look at the object here, and then do the, and also he also proved that there is a Verschubung on this, and he gave, using this space, he gave a simpler proof of N-ometa. I don't know whether he did a simpler proof here also, for the map also. But anyway, simpler proof of N-ometa. The psi, you fix a, yeah, P is the polynomial, yeah, Hilbert polynomial. So given that bundle, so all these bundles will have same Hilbert polynomial as the polynomial of the trivial bundle. Okay. And so in that RP space, you do all this game. I'm not getting into the details, because when you do and take the orbit and take the closure, you may pick up some few components. And then you have to argue a little bit, but not much more. So main idea is already here. Okay, that shows there are finite bundles. Okay, so that gives you, like, how do I pass from a stratified bundle to finite bundles? So conclusions on finite bundles. But then still, how do I get an isomorphism? So given a bundle on Y, the stratified bundle also has a map. So given a bundle on Y, I can pull back and get a bundle on X. Now, how about reverse? So the problem was constructing on kind of by hand a bundle on Y. Given a bundle on X, stratified bundle on X, I wanted to construct a bundle on Y, okay, which does the job. In other words, whose pullback is this? That gives you the equivalence of categories. Okay. So how do I go about getting it? Given a stratified bundle on Y, how do I get a bundle on X? So for this, we had worked out a sequence of, in a series of papers, we have done a few things about the sheaf theoretic behavior, the bundle behavior of, for a finite map like this. And we called it genuinely ramified map. So theorems, f from X to Y is called genuinely ramified. If any of the following satisfied. A, phi1 etal X surject onto phi1 etal Y. B, you take, so this is, first of all, F must be finite separable. A finite separable map is called. You take F over star OX and look at degree 0. This must be equal to 4. Okay. Third, X cross X over Y is connected. Okay. And there are a few more this thing we have seen where we have done. One is if and only if in other words, these are all equivalent. I'm giving it as a definition, but they are all equivalent. That's what it means. One of the following is satisfied. Yeah. If any of the following. Phi1 surjection. Phi1 surjection. The beta subbundle of F over star O is OY. The other one is this fiber product is connected. And there is other one is because it is F over star of O, that naturally contains a connection. And you can take this connection, usually it is singular. Around the ramification, they will become singular. So you can ask where the maximal subsheaf, where it becomes regular. Obviously, on OY, it will be regular. It's the same D. So that will be regular. And do you say that the maximal subbundle, where the maximal subsheaf, where this natural connection of F over O is regular, is OY. So in terms of the connections also, one can give a equivalent definition. But anyway, we are really concentrating on this part. It is this that gave us using adjunction and lot of, this is really the sheaf theoretic, bundle theoretic statement. Okay, so genuinely ramified if and only with lower sorrow. There is also more. There's something, we proved one more interesting statement. Pardon? What is it? That's a mu max, kind of the maximal subbundle. Because you can prove, that's right, degree 0 subbundle, and you can prove mu max is 0. So this is the beta subbundle. This is the first part of the harder analysis. In fact, okay, so I'll just tell you the proof that it's mu max is 0, because if there is a, you look at any f is negative. That's right. Or there, that's right. So in fact, there's also, you can see this. So f lower star Ox is the same thing as home f upper star f comma Oy. No. Ox, and this is Ox. So if this mu is bigger or more positive, then there will be a map, and semi-stable pull back to semi-stable. So there will be a map of a higher mu to O. So that's not there. So in fact, this I can, instead of O, I can also replace it by any W. Any W, and this adjunction will tell you that the mu max of F lower star W is degree times the mu max of W. So that cannot go beyond that. So for instance, if semi-stable of degree 0, the push down has degree 0 and less. Okay. And moreover, if it is genuinely ramified, what you get is home VW is home F upper star V F upper star W. So for instance, you take finite bundles. Take the home here. When I go up there, the homes are same. So it's actually the Tanaka is the categorical map, the homes preserved. So this is also important for that purpose. Okay. So this is proved purely using sheaf theory. The idea is one doesn't use any much deeper ones, but just sheaf theory and the direct images and taking the harder version filtrations. Any semi-stable ones. In fact, there is one more statement here. Maybe I should also do E. Every stable bundle. My God, I can't even write. Wait, I'll write there. So this took us some time, but I'll put an E there. So this requires other degrees. For instance, for a genuinely ramified, it's not enough to do only for degree 0. In the degree 0 alone, you may not see that there is a stable bundle pulling back. So to get that, you actually need all stable bundles. Especially you can see that from elliptical to elliptical, take a isogeny. Then if I take only degree 0, there are no stable bundles. And line bundles anyway pull back to line bundles. But it's not genuinely ramified. Because pi lower star is the degree 0 is the full bundle itself. Because they are semi-stable. And in fact, here the proof is you take this subbundle. The idea of the proof is that you take this subbundle. This whole thing, this contained in F lower star Ox. F lower star Ox is already sheaf of algebras. What you essentially prove is that this is a sheaf of subalgebra. And reason is exactly what he said. But this degree 0, other degree 0 part. So the tensor. But the tensor, you have to do a little bit of work. Some home and some little bit of extra work is needed because you are in characteristic P, but still it's correct. That it takes into degree 0. So F over star O degree 0, tensor F over star O degree 0 maps into F over star O degree 0. And hence it's a sheaf of algebras. I can take its spec. Once I take its spec, you will see it's an étal map. So that is how the equivalence comes. Yeah, now what? Yeah, so in other words, this pullback. So the natural way of pulling back is actually a home even from the category point of view. The categorical home actually takes it to categorical home. Degree 0, yeah. That's right. Yeah. But that requires something. Now, so this is not always true for push forward and this. So this requires an isomorphism. So I'll give a criteria. So this is a theorem. Okay, let V be a vector bundle. Let's say semi-stable or stable. And in fact, degree doesn't matter. Semi-stable bundle. Okay, but let me put of degree 0. Then V is a pullback. If and only if rank of F over star V 0. Here there is a bit of difference, I'll tell you. That should be equal to rank V. See, if I take a degree 0 bundle, the push down may have only negative things. Okay, you may never have a degree 0 part. So if it is not there, then it is 0. So I'm actually looking at the 0 part of it. Whether it is just 0 or empty, or if it is genuine. So if it is genuinely there, I mean the rank is equal, then the pullback of this equal to F is genuinely ramified. Yeah, F is genuinely ramified. Genuine ramification automatically takes care of the other two finite subprevalence. When that happens, then I can recover the bundle. So a bundle above, I can tell you when it is actually a push forward, I mean a pullback. And now I'll come back to this. First of all, for FP bar, you are already done. I can just apply the same theorem. There are finite bundles, and then you will see that. So it's start with arbitrary bundle and take a degree 0. But then, so I want to compute its rank. But then you already see that the finite bundles are already dense there. Okay. Using that fact, what you'll get is that this degree 0 part itself should have the same rank, and hence the bundle must be full rank. Okay, but in the for Shubham. Now, if it is not over FP bar, then you need to play a spreading game. So there are two steps in none. One is that when you do the spreading game, you have to make sure that over a general point is good enough on the spreading. Over a general point, the map from XS to YS remains étal isomorphism. And for FP bar, there I already know that stratified is an isomorphism. From there, I have to say over the T, generic point of the T, or over the original field itself, it is actually is a pullback. So if I start with the stratified bundle, restrictions are stratified, I can apply this. Now I come back to this. It's kind of Harder-Narasimhan is sort of, there is a relative Harder-Narasimhan. So you take F over star O, and then for a generic point, the degree 0 part, the Harder-Narasimhan part of is actually restriction of the Harder-Narasimhan from the total. And then for a general point, I know it has the same rank. And hence the pushdown actually have the same rank. And hence it's actually a pullback. So this is the final. And that's the rough idea of what's been done. So the point is moduli, we will replace it by representation theoretic moduli so that we don't get into extension issues. So it's done in one stroke. And then it is really these kind of chief theoretic analysis that went in throughout. So we were able to possibly give you what bundle I'm expecting. Yeah, with that I'm done.
Any questions or comments? If there are no further questions, let's thank the speaker again. I'll present the ISR Mohali model to the speaker.
Thank you.
Okay. So welcome everyone to the afternoon session. So it's a great pleasure to have Professor Arno Bovil give the first talk of the session on the series cycle. Over to you, sir.
Okay. Can you hear me?
Yes, we can hear you.
Okay, so I'll start. So thank you very much for the invitation. I'm sorry I couldn't come in person. I see I have many old friends in the audience, including, of course, Kapil. Well, I will try at least to give this talk. So the main tool I will consider is algebraic cycles mod algebraic equivalence. So let me recall briefly what this is and also fix the notations. So I will always consider the smooth projective varieties X. The group of p-codimension cycles is simply the free group on the irreducible subvarieties of codimension p, like this. In itself, it's not a very interesting group. It's a free abelian group, but it becomes very interesting when considered with various equivalence relations. And the one I will be concerned is algebraic equivalence. So unfortunately, there doesn't seem to be any canonical notation. I will use simply A for algebraic. So this is a group of cycles modulo equivalent algebraic equivalent, sorry. I won't give a formal definition, but let me just draw a picture. We say that two cycles are algebraically equivalent in the appear in the same algebraic family. And typically an algebraic family means that we have a parameter space, B, which you can think of in a smooth curve. And we have a cycle of over X times B of a dimension 1 more the dimension of Z. And we pick up the trace on X at two different points of B. So we have a cycle ZA and ZP, and we decrete that they are algebraically equivalent. So it's a very nice equivalence relation. And the quotient, which we denote by A star of X, is a ring with the intersection product. This is a classical object. I mean, this was known from by the Italian geometer, in particular Severi. So sometimes the formulation is sometimes hard to decipher for us, but definitely there. And it has been formalized in modern language by André Weil in his foundations. So despite it's a very natural object, it's still poorly understood. It's quite difficult to understand. One tool to do that is to compare with cohomology. We have a cycle class map. If two cycles, Z and Z prime, are algebraically equivalent, then they have the same cohomology class. So we get a map, called a cycle class map from AP to H2P with Z coefficients, which hopefully will help us to understand AP of X. Let's look at some easy cases. Well, there are basically two easy cases. The first one is when we look at zero cycles. So we take P dimension X, and we look at finite integral combinations of points. This is AP of X. Now, 2 points of X are algebraically equivalent. We can take X itself as a parameter space to write the equivalence. So the cycle class map in that case is simply the degree of the cycle, of the zero cycles, when we identify H2P with Z. And this map is an isomorphism. A little more subtle is the case of divisors, P equals 1. Then we have this map to cohomology, to H2, which is injective, and the image is what is called the Néron-Severi group, the group of classes in H2, which are represented by algebraic cycles. So you see that in these two cases, the class map is injective, and so it's very natural to ask whether this is true in general. This, in which case, I mean, we would control AP of X. I mean, describing the image is the content of the Hodge conjecture. It's a different problem, but here we are asked whether this is injective. And it seems that people in the 50s would think the answer is yes. For instance, there is a nice lecture by Samuel in the ICM in 1958, where he mentioned this injectivity as an interesting conjecture. So I think it came as a surprise when Phil Griffith, at the end of the 60s, showed that it's not always true, and even more, I mean, it's very often not true. He proved that for many hypersurfaces, in P2P, so odd-dimensional hypersurfaces, this cycle class map is not injective. I will not give a precise statement because it's a little bit technical. I will give an application in a few seconds. But let me say that the kernel of this is a map from this map here, from the cycle class map. The kernel will be called the Griffith group for obvious reasons, GP of X. Now I will slightly switch notation and do everything over Q. I will take Q coefficients. I'll say a few words at the end about Z coefficients. It's a quite different problem, and for now on, I will stick with rational coefficients. So I have this exact sequence. I still denote AP of X now, the group of algebraic cycle with rational coefficients, mod algebraic equivalence. So I have this cycle class map to rational cohomology, and the kernel is by definition the Griffith group. Okay, and let me give an example which follows very easily from Griffith's general setup. Let's take a general hypersurface, smooth hypersurface, of course, of degree 5 in P4. It can be proved that it contains a high number of lines, 2,875 here, and they are all linearly independent in the Griffith group. Note that now this is a Q vector space and of dimension at least 2,000 and something. In fact, more is true. Later, in 1983, Clements proved that this is an infinite dimensional vector space. What he did is use line, then conics, and rational curves of degree 3, and shows that there are enough of all of this to get infinite dimension. And this was, in fact, generalized by Clairvoisin for a general Calabi-Yau threefold. I won't make precise what I mean by general, but this is somehow what you expect for a Calabi-Yau threefold. Okay. There is another counterexample, which I think has been questioned immediately after Griffith's example. It's of a different nature. We start from a curve, let's say of genus at least 3, and we embed it in the Jacobian by the Abel-Jacobi map. So we choose a point P, and we consider the image of, we associate to a point X of C, the divisor class of X minus P. Now we can, we have a -1 involution on J, so it's an abelian group, and then we consider the cycle difference of C and its opposite, modulo algebraic equivalence. We observe that it does not depend on the choice of P, because, I mean, if you move P, clearly you get an algebraic family of cycles, and then they are all, by definition, algebraically equivalent. But there are also cohomology, I mean, this cycle is cohomologically trivial, because the -1, the operation multiplication by -1 on J, it's quite easy to see that it acts as -1 on H1, and H2 is canonically the second wedge product of H1, and therefore -1J acts trivially on H2. So when we minus C has the same class as C, and therefore this difference, this cycle, belongs to the Griffith group of codimension G-1. And now the natural question is whether this cycle is 0 or not. And the theorem of Chza in 1983 is that for a general curve C, remember it is of genus at least 3, this cycle is different from 0. So this is a very nice example. This is actually a rather easy proof, like, using some Hodge theory, and basically Griffith's method, I should say. Now we observe that for a hyperelliptic C, this is false. Its Chza cycle ZC is actually 0. Even more, if we choose correctly the point P, the cycle itself is 0, because if we choose for P a point which is invariant under the hyperelliptic involution, the Weierstrass point, if you prefer, then C is actually equal to -C because of this simple relation. If you take a general point of -C, so it's of the form P minus X, but this is linearly equivalent to sigma X minus P in J, which is a general point of C. So we have equality of these two sub-varieties, and therefore this C is 0. So now a very natural question which arose at that time, which was explicitly asked by Herb Clemens, is whether the converse is true, whether the vanishing of the Chza cycle is equivalent to C being hyperelliptic. And I mean, the question has been, I would say, dormant for about 40 years, maybe forgotten, till a few years ago, where with Chza, we gave a precise example of a non-hyperelliptic of genus curve of genus 3, for which the Chza cycle is 0. This is curve y cube equal x4 plus x, and it is 0. Now that C is a smooth, I take of course a smooth completion of C. It's a 3-to-1 cover of P1, branch along the point here. And so what is the idea? The main ingredient of the proof is that this curve has an action of Z mod 9. And namely, you take a zeta primitive ninth root of unity, and you have a Z mod 9 acting on C by the formula here. You can check easily that this preserves the curves. All the two terms are multiplied by zeta cube. And the key point of the proof is that the quotient J mod G is uniruled. It's a uniruled threefold. We prove this using the so-called Reed-Tile criterion. It's not difficult. And once you have this, I mean, it's not difficult to show that the Chza cycle is zero. That would be very easy if J mod G were smooth. Then we look at the covering map. It induces an isomorphism of the Griffith group of J mod G here onto the invariant part of G2J. But it's not difficult to see that for a uniruled threefold, the Griffith group is zero, basically because it's dominated by a product P1 times the surface, and for surfaces, the Griffith group is always zero. And since the Chza cycle is invariant under G, it belongs to this, and therefore, by this isomorphism, it's zero. It's a little more complicated because J mod G is at some singularity, so we need some Hodge theory to take care of the singularities. Now, shortly after proving that, I realized that this property that J mod G is unirule is extremely rare. It's in fact, I had a partial result, which was improved by Raisa Serova, a student of Kostya Shramov. And we proved that there are only 3 non-hyperelliptic curves with this property, that J mod G is uniruled. 2 with Genus 3, this one is 1 and there is another one, and 1 with G4. So there is no way to extend our method to other cases. This is really a sort of exceptional case. Nevertheless, after our paper, a number of other examples have appeared. I will list them chronologically. So I think the first was Lilienfeld and Steinman. We took the other genus 3 curve with the property that J mod J is unirule. See this guy here. Oops. Sorry. And they use the same method and prove that this one also has a vanishing Chza cycle. Then later, with a different method, proves that this so-called Amber curves in genus 5 have also vanishing Chza cycles. Then there was a paper by Chu and Zhang, maybe 2 years ago, with a sort of giving a criterion which covered a number of curves, or I think all the curves before, and also the Bring curve in genus 4, and the so-called Macbeth curve in genus 7. And finally, maybe 6 months ago, or maybe more, almost 1 year ago, there was a nice paper by Laga and Schnittban, which essentially covers all the previous results and with some very nice method. In particular, they show that all curves of this form, these are sometimes called Picard curves. So the triple covers of P1 branched along 5 points. There is also a point at infinity. And all these curves, the smooth ones, of course, have vanishing Chza cycle. I mean, my aim is to explain the ideas of this paper, which I think are quite nice. Before you are certainly entitled to ask, why do we need so many examples? I mean, we have one or two. It proves that definitely the converse of a Chza result is not true. Why do we need so many? Well, to try to convince you, I'll try to explain that this property of having vanishing Chza cycles is quite important. It's equivalent to some other very important properties for the curve C. One is the following. This is about the so-called modified diagonal cycle, sometimes called the Gaussian cycle. I think they were maybe the first to consider these cycles for curves. So you see a cycle now is a triple product of the curve C, and then codifferentiation 2. So this is a one-dimensional cycle, and it's we take all the small diagonals of C with sign. So first the small diagonal, three points with x varying, or the locus of x, x, x. Then we fix a point P, and we take x, x, P, x, P, x, P, x, x, and then x, P, 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 x, A, and so on. It's very easy. It's an easy exercise using the Quinet formula to show that the cohomology class of this cycle is 0, and therefore it belongs to the Griffith group, G2 of C3. Therefore, we again have the question of whether this cycle class is 0 or not. And okay, before I should say that it has been, you can define this cycle also for any smooth projective variety, diagonal and so on. And it had been studied quite a lot, and I put a few names here, Moonen, O'Grady, Voisin, and also we have studied it for K3 surfaces in our paper with Claire. And a nice result, which is due to show with Zhang. This is not the same Zhang as we had before. This is another one. The vanishing of the Chza cycle is equivalent to the vanishing of the modified diagonal cycle. This is also equivalent to something which I will not define, I will not use it in the rest of the talk, but which I think is a very interesting notion. This is called multiplicative Chow-Quinet decomposition. I'd say a few words later about what this is. This is something which sometimes exists, sometimes not. For a curve, it's rather rare because it exists exactly when the Chza cycle is 0. And we will see more equivalent properties of the vanishing later. So this gives, I think, for me, this proves that this is a quite interesting property of a curve, this vanishing. And so I think it's justified to try to find examples for which it holds. Just one remark. I am working with cycles mod algebraic equivalence because it's, for one thing, it's simpler, and also it's the original approach. I mean, the Chza theorem is really for cycles mod algebraic equivalence. Otherwise, the Chza cycles varies. I mean, it's not independent of the choice of the point. Actually, the result extends to the Chao ring, but with a more technical complication. So to avoid technicalities, I will stick with the algebraic equivalence point of view. Okay, now I want to explain a little bit these ideas of Lagrange-Tillman. And there was something before in fact, before the work with Chza, and this is what, in some sense, motivated work with Schoen. This is a remark that I made maybe 5 years ago. So let's go back to this particular curve C, y cubed x4 plus x, with its section of the group Z mod 9. And I observed well, this is 4 years ago, that if you take the third cohomology of the Jacobian, there is no invariant piece under the group. So you may ask, why the hell ask something like that? Well, there was a motivation. If we choose for P, we know that P is used for embedding C into the Jacobian. Choose the point 0, 0 here, which is clearly invariant under the group G. Then C and minus C are invariant under G, and so the cycle, the C, is invariant under G. Now there is a map which associates to such a cycle. Its image is a certain complex torus called the intermediate Jacobian of J. Again, this is something I will not use in the lecture, so I don't want to give further details. But this, in particular, let me just say that this vanishing here implies that there is no invariant classes in the intermediate Jacobian of J, and therefore this Abel-Jacobi image of the Chza cycle is 0. This is what I wanted to prove, because there are some very general conjectures of block Beilinson, which would imply that the vanishing of this Abel-Jacobi image suffices to prove that the Chza cycle is 0. I should say that these conjectures are completely out of reach, so I do not claim that, but this was a first step towards the vanishing of the Chza cycle. And this is why we started with Schoen to prove really the vanishing. Let me show you what this is, what we have this vanishing, because I think this is important for the cycle. What is H3 canonically is a third exterior power of H1, right? And H1 is of the form V plus V bar, where V is a space of holomorphic one forms on C, and V bar is zero. See, just a way of writing down the Hodge decomposition of H1. Okay, let's see how this group G here acts on V. It's very easy to find a basis of holomorphic one forms on this curve C. You see, you get these three guys here, and you can check that they are holomorphic, and clearly they form a basis. Let's look at the eigenvalues of the generator, which acts like this. So you see x is multiplied by zeta cube, y by zeta. So here we get zeta, here we get zeta multiplied by zeta cubes, that's zeta 4, and here we get zeta squared. Then we have the conjugate, so I just put zeta minus, excuse me, minus 1, minus 4, minus 2. And now it's a nice exercise to see that each time you take three different values here, the product is not equal to 1. This is not, I don't know, maybe surprising, because 6 choose 3 is 20. So I have 20 products to consider, modulo 9, but still none of them is 0 mod 9. As an exercise, I mean, you can notice that if you take these guys here, you get 3 different exponents. The sum is odd, it can never be 0 mod 9, and then you consider the case where 2 where you have, say, 4 and minus 4, and again, it cannot be 0. So it's a very simple exercise. So this proves that there is no invariant vector in this C vector space under the action of G. So as I said, this implies that the invariant part of the intermediate Jacobian is 0, so the Abel-Jacobi image. But Lagrange-Tillman proved much more with no conjecture. This simple vanishing here implies that the Chza cycle is 0. Do not assume any conjecture, as you will see. This is a nice implication. This applies essentially to all the curves I've mentioned above. I should mention that this condition, vanishing of 3G, becomes very restrictive as the genus G grows. And as I wrote here, the current record is J equals 7, the Macbeath curve. It might be that there are some higher genus curves with this property, but certainly not. I mean, I don't think I have a proof, but I'm sure that for G large enough, this cannot happen. So unfortunately, this will give only low genus examples. I will go back to this at the end. Okay, let me give in what follows. I mean, I will give an idea of the proof. And there are 3 ingredients which are sort of slightly sophisticated, I would say, and which are all very specific of abelian varieties. Well, now let me consider a general, I mean, a G-dimensional abelian variety, X, and I will consider X is a group in particular, so we have a multiplication by integers. So I will use this boldface K to denote multiplication by K, and this is an endomorphism of X. In particular, it acts on cohomology, on algebraic cycles, etc. The first ingredient is the fact that this endomorphism, K star, viewed on either on the Chow group or on the group of cycles modulo algebraic equivalence, diagonalize simultaneously. That means that we have a decomposition of AP of X. As remember, this is a Q vector space. I'm always working with Q coefficient. So it's a direct sum of Q vector subspaces, APS, with the property that on APS, K star acts as K to the power 2p minus s. Yeah, the notation is maybe not so good. You will see later that it's sort of maybe not the best. I chose this because conjecturally and also for certain value of p, S negative should not appear. So we should have a decomposition of the form AP of X, AP0, and so on. 0, 1, going just to p minus 1. And this corresponds to what is called the conjectural block Beilinson filtration. Namely, this space here corresponds to cohomology classes. They behave, when S equals 0, you have this property. This corresponds to the behavior of cohomology classes. Then you have some lower index or higher index cycles which behave like intermediate Jacobians, and then you go lower and lower in the group of in the space of algebraic cycles. So that's roughly the idea. In particular, I'm interested in the class of the curve C embedded in J. And in that case, it's known that we have no negative indices. So we have this space and we have this decomposition here. Okay. Then we go have the class of curve C, which will decompose accordingly to this splitting. So we have a component C naught, which you should think of corresponding to the cohomology class of C, then C1 and so on, Cg minus 2. Now I can complete what I said about equivalence of the vanishing of the Chza cycles. The proposition, I think I didn't put the name. This is essentially again due to Zhang, to say that this is 0, the Chza class is 0, is equivalent to say that all the Ci vanish for I greater than 0. So we just have the 0 index class. It's also equivalent to ask just that, sorry, C1 is 0. None of this is trivial because if you use the property, maybe I should go back to the definition of here, the action of K. You can apply this with K equals -1, and you find that -1 star will act trivially when S is even, and as -1 when S is odd. So going back here, again, this is 0, this is C minus C. This is, by definition, equivalent to say that the I is 0 for all I indices. Odd indices, for I odd. Okay, so these two properties are in between. Of course, this implies C1 0, but it's not, nothing is obvious. It's not obvious that it suffices to, this implies all Ci 0 for I greater than 0. But that's true. So what we must prove now, have the result, is that the vanishing of this invariant part here implies that this class C1 is this small part of the decomposition of C is 0. So that's the first ingredient. The second one is due to Denninger and Murray, who, using this this previous work, they obtain a decomposition of the motive of X. Now, I certainly don't have time here to explain what is a motive. Let's say I'm looking at motives for algebraic equivalence here, because this is what I'm working with. Could as well be for Chow motives. If you don't know what is a motive, you could think of a motive as being a piece of an algebraic variety defined by some geometric means. I mean, I will not say more, but it's essentially what you should. It's a sort of direct summand of an algebraic variety. And in the case of abelian variety, we have a complete decomposition of the motive of X as a direct sum of motifs with a certain weight. And this weight is characterized by this property that K upper star acts on this motif as K to the I. By the way, the motif is an abelian, has a, I would say, this decomposition is a Z-linear decomposition. So a motif has an action of Z, which makes sense here. This implies in particular that this endomorphism, K star, acts on what do you say? As I forgot, sorry. Here I consider cohomology of the motif. So H star of hi of x and A star of hi of x. Hence, since it's multiplication by ki, it means that H star or hi of x is just the ordinary cohomology, let's say with q coefficients of x. And now, because of my special notation, because here multiplication by k corresponds to multiplication by k to the 2p minus s, we see the AP of hi is AP with this sort of shift 2p minus I. This is where my notation is perhaps not optimal, but okay, this is the way it is written now in the literature, so we don't change it. So we should remember this point that we have AP of hi is AP of 2p minus I. Parenthesis, this is exactly what is called a Chza decomposition. And in fact, in that case, it is multiplicative in the sense that I mentioned before. So this a Chza decomposition is decomposition of the motive of X with each segment corresponding to one cohomology group, this property here. This is again, I will not use this in the rest of the talk. Okay, so let me go back, continue with the proof of the Lagrange-Needman theorem. So remember, now we consider our curve C. Now C1 was in AG minus 1. Okay, by definition, since I take index 1, this is this index 1 here, and it is invariant under G, so is it in this part here. Now, by what I just wrote before, this is AG minus 1 of the motif H2G minus 3 of J. So just this shift between indices here, which is. So what we would like to prove, in fact, is that this whole motif here is 0, which will, of course, imply that C1 is 0. And this is a claim that this motif is 0. The third ingredient, which is very important, is a beautiful result of Kimura, which says that the motif of an abelian variety is what he calls finite dimensional. Again, I will not give a definition, it's a bit technical. I will tell you the main properties that they use. And I should say this is very particular to abelian varieties. Very few varieties are known. It is conjecture, I mean, Kimura conjecture, that it is still an open conjecture that all smooth projective varieties have a finite dimensional motif, but this is very far from being known. In particular, this implies that this motif, this fixed part of the motif, is still finite dimensional. The direct summand of a finite dimensional motif is finite dimensional. Now, the beautiful property, very specific to finite dimensional motif, is that what people say is that cohomology is conservative. Namely, if the cohomology of a finite dimensional motif is 0, this implies that the motif is 0. So we just have to prove that the cohomology of this motif is 0. But what is the cohomology of this motif, H star of this? By what I wrote before, this is just the cohomology of weight 2G minus 3 of J, invariant under G. By Lefschetz theorem, H2G minus 3 is isomorphic and in an equivariant way to H3 of J. So it's the same thing as H3 of J invariant. The hypothesis is that this is 0. Therefore, our motif is 0. And C1, which is an algebraic cycle on this motif, is 0. This is a proof of the theorem. Okay, stay a minute with this. We proved in this way that C1 is 0. And as I told you, this is sufficient to imply that the Chza cycle, the C is 0. As I said before, they have a much more general result, well, more general results, which is the fact that this condition can be weakened at least for a particular type of curves called the Picker curves. And this is a curve of this type. This is just the triple covers, Galois triple cover, triple covers with group Z mod 3 of P1 branch along 5 points. So it's a smooth curve again of just 3. This is a two-dimensional family. You can, it's easy to see. All of them have vanishing Chza cycle. How do we prove this? Again, this is, I think, a very nice idea. So this is a theorem, which I wrote again. The idea now, we just have an action, we don't have Z mod 9, we just have an action of Z mod 3 acting, of course, on Y, by multiplying the Y by third root of unity, rho. It's no longer true that H3J is invariant. In fact, it's two-dimensional. But the holomorphic part, the H3 0 part, invariant, is 0. Let me show you briefly why. Again, we look at what is H naught omega 1J, canonically isomorphic to H naught CK, the space of holomorphic one forms on C. It's easy to write a basis, here it is. And you can see that when you multiply Y by rho and you leave X invariant, the eigenvalues which appear are rho, and rho square. When you take wedge 3 of, maybe I should start with 0. What is H naught omega 3? It's wedge 3 of the space. It's a one-dimensional space with basis, the wedge product of these 3 forms here. So you see the eigenvalue is rho times rho square. It's rho, it's not 1. So this invariant part is 0. So we are left with a Hodge structure here on H3 of weight 2, 1 plus 1, 2 with dimension V, 1. So this looks very much like the Hodge structure of an elliptic curve. And in fact, it's not difficult to show that this is isomorphic to the Hodge structure of the elliptic curve written here, C mod Z of rho. If you prefer, this is the elliptic curve y square equals x cubed plus 1. The minus 1 here is just conventional, it's because of weights. A priori, this has weight 3, this has weight 1. So to put everything in weight 3, we multiply this minus 1 is just that we consider this Hodge structure here as a weight 3 Hodge structure. Okay, so that's not difficult because we have this action of Z mod 3. Then, what is this isomorphism? It's given by an isomorphism of Hodge structure. It's given by a cohomology class. You use QNet formula to say that this corresponds to a class in H4 on G of the product of these two varieties. And the fact that it's an isomorphism of Hodge structure tells you exactly that this cohomology class is of type 2, it's a Hodge class. Now, here comes another miracle, is that the Hodge conjecture holds for this abelian fourfold. So as proved by Chza. Again, this is very particular to the situation here. This is because we have a complex multiplication here, both on J and rho, but it's true. Therefore, this Hodge class here, this class of type 2, is actually an algebraic class. It comes from an algebraic cycle. This is the content of the Hodge conjecture. So an algebraic cycle, that means that you give an isomorphism of motifs of this S3J invariant onto the motif of the elliptic curve. And therefore, let's go back to our curve C1. It was in this A2J1 invariant. So it was, which is A2 H3 of J G, right? This is what we had before. We had 2G minus 3, but here G is 3. So 2G minus 3 is 3. Using this isomorphism here, this A2 is simply A1, codimension 1 cycle. I mean, that means 0 cycles on the motif of rho. Again, using this relation between A of motifs and A of the variety, we see that this is 0 cycles on rho, and this is the index 1 part. But I mean, the group of 0 cycles modulo algebraic equivalence on a curve is just Z. There is no, the 0 part is 0, and there is no index 1 part, so it is 0. And that's how you prove the Lagrange-Millman theorem, this theorem 2 here. So you see you have many sophisticated ingredients. This decomposition of the motif of an abelian variety, the finite dimensionality of the motifs, and finally the Hodge conjecture for this particular abelian variety. Okay, let me finish with some questions. First question is, as I mentioned above, all methods we have so far work for low genus. Things we record is a Macbeth curve of genus 7. Are there examples in higher genus? I mean, this would be, I mean, is there a bound on the genus for which this happens, or I have no idea. I mean, I would not make a conjecture. I can only state that the methods we have don't work in higher genus, but there could be, of course, another method. Another question, from the beginning, almost the beginning, I used rational coefficients. Of course, things make a lot of sense with, originally they make sense with integral coefficients. This is a completely different problem, and which is also very interesting, but for which we have very few results. For instance, I mean, all the methods I've mentioned use rational coefficients. There is no example known. I mean, it could be, but in all the examples were known, we know that GC is torsion here, because when we tensored with Q, it gives 0. But we don't know whether it also really some new methods are needed. Okay, I think I will finish here and wish a very nice birthday to Kapil. Thank you.
Are there any questions?
Of course, for hyperelliptic curve ZC is 0 always, right? I mean, even with integer coefficients. So your point is that it's.
I don't know. I don't know. I mean,
Sorry?
I couldn't make a conjecture in other sense. I mean, it's, for instance, in our examples with Chad Schoen, we can prove that 9 times ZC is 0.
Okay.
But
Right.
whether 3 ZC is 0, we don't know. And I will not make any bet.
So the other question I had is there's this infinite dimensionality thing. So maybe one could also look at whether, the Chza cycle Madhav proved generates an infinite dimensional group by using the automorphisms of the function field of moduli space for abelian varieties. I don't know.
Yeah, well, maybe I should have mentioned that for abelian varieties of dimension 3, there is a very nice paper of Nori who proves that for a general abelian threefold, again, the group of cycles mod algebraic equivalence is infinite dimensional.
Right.
I don't think this is known for higher genus. I mean, it's I think it uses in a crucial way the fact that an abelian threefold is always isogenous to a Jacobian, which is no longer true in higher genus. So I think this is still an open question. I don't know if
What I
Nori
was
is.
wondering is whether you can expect that you will get finite dimensionality for the something other than hyperelliptic.
You mean for the Jacobian? Okay, see, I understand the question. That's a good question. I have no idea about the answer, but yes, that's a nice question.
Thanks for the nice talk. Yeah.
Mhm.
Are there any questions? All right. If not, let's thank our speaker for a wonderful talk.
Thank you.
So there is a question in the chat. What about the could you see the chat question? So it says, what about the case of higher dimensional modified diagonal cycles in the group, for instance, in CH3, HOM C5?
Just a minute. So where should I? So could you repeat the question? The diagonal cycle in?
The question is, what about the case of higher dimensional modified diagonal cycles in the group, for instance, in Chow group 3, HOM C5? I think so.
Okay, I get.
Yeah.
I get the question. I'm afraid I don't know the answer at all. But that's again a good question. That's something which one should certainly look at, but I have no idea. Sorry.
Okay. All right. Okay. Then we'll break now. Yeah. Thank you, Professor, for again joining us.
Thank you.
Okay. So welcome back to our second session. So Professor Rajan will give a talk on non-lacunarity of coefficients of linear combinations of L functions of IID Galois representations.
Yeah, so okay, so first of all, thanks to the organizers for the invitation to come here and give a talk. And of course, it's a great pleasure to be here. Kapil, I got to know him maybe around 1981 or some such, when I got to hear from various people that here is this person who's 2 years senior to you in Kanpur IIT and you should go and meet him. And yeah, but so he had, of course, a amazing reputation by then that he knew a lot of mathematics. And then I talked to him, and then, of course, he was saying you should read Griffith's arrays and various things, which by the time he had left IIT Kanpur, he already seemed to know a lot of it. And in my final semester, I tried very hard because I had also gone for this vector bundles thing. And then tried really hard to learn something or the other. One has to know all these things before getting out of it. And it stressed me out so much that I was sleeping 16 hours a day and didn't learn anything at all. But later, as it happened, then, of course, joined TFR. And, Kapil, Nitin, Dipendra, Venki were kind of immediate seniors, and we kind of looked up to them. It was, of course, again, not to say it's not at all easy. These people are kind of, they seem to know almost all of mathematics or whatever it is which we got to interact with. And I was, in my second year, asked to share office with Kapil and Nitin. And I remember very distinctly in one time I said, I'm not going to be wedded to them for the rest of my life. That would be disaster. So then I finally decided I have to do other things. So went rock climbing with Inamdar, and which is not. But there are two things which I like to thank Kapil for, but one which I never followed to some extent. It is that immediately after a lecture, we would attend and come back. He would say, let us go through the lecture immediately, which was, revise the whole thing. So, but that I've now been able to follow. But there was another aspect which I thought was very useful to me, which was that we used to go out into the city, and there was once while we are in a bus or something, he said, what you should do is we were sitting, the bus was crowded, so we are sitting separately and inside Bombay only somewhere. And then he says, the easiest thing is to pick up some problems or other things and keep thinking about it. Don't, whatever, spend your time, looking at the scenery or VT going past or something. But, and yeah, that was, I think, pretty useful. So, but I kind of realized when I was coming for this thing that I had lost that. Of course, it needs to be trained, but so that was one thing which I really thank you for that. And yeah, I also want to thank another member, Dinakar, for the mathematics which I'm going to talk about today. Was heavily influenced by his. Earlier I had some work with Ramurthy on multiplicity for GL2, conjectural, but I went and was with his guest for a month, and then he said, no, don't think only of GL2 or analytic side. You have to think of GLN, L-adic, and the most general. And he handed his reprint, so that was extremely useful. And later, it was kind of when I saw through Sayre's paper, I kind of realized the solutions to some of them. Okay, so what we want to do is to talk about non-lacunarity. So I'll say what the motivation. There are two motivations. So motivation one was what are called the Lang-Trotter conjectures. So the easiest thing is to state it for, suppose take E is an elliptic curve. Or say over Q. And then you can look at, say, the points of, suppose assume P is a good prime. You can look at the points EFP, reduction mod P of the elliptic curve. And this has cardinality equal to, say, P plus 1 minus AP E. And so if I assume P is greater than or equal to 5, I will not get into that. So then one knows that E has supersingular reduction. I'm assuming P is a good prime. Reduction at P, if and only if by the Weil estimates, AP equal to 0. Okay, so Lang and Trotter, what they were trying to look at is the collection of primes P of supersingular reduction. So what the Lang-Trotter conjecture, that if I look at the cardinality of P less than or equal to X, so that AP equal to 0. So of course, the prime number theorem will tell you it should be like X upon log X. So what this is saying is there should be an epsilon, of course, say X upon square root of X to the power half plus epsilon. Yeah. Okay, the constant will depend on epsilon. So let me say, why should I say that? Less than or equal to some constant depending on epsilon times X to the power half plus epsilon. It might be X to the power half upon log X or whatever it is, but something like that. So this is one motivation. So for instance, instead of the elliptic curve, you can look at higher weight eigenforms. And the motivation number 2, which is kind of related to this, is what is called the Lemmas conjecture. So if you look at the discriminant modular form, the Ramanujan form, so this is a discriminant for the moduli, the discriminant. Of the moduli space for elliptic curves, discriminant. Let me just call it the discriminant modular form. And then, so it has a Q series expansion, the famous Q plus tau 2 Q squared. And these are the Ramanujan tau n's. And Lemmas' question is that tau n is never 0. For all, yeah. Yeah, so these are the kind of questions which one would like to throw some light on. And what, part of the thing is to say is that one of the things is that these questions are still widely open, especially Lemma. So it's kind of, and more, this thing more generally, for instance, more generally meaning, if I take F is a higher weight eigenform, weight greater than or equal to 4. This is weight 2. This would correspond to, this is weight 12. So then you can look at the Hecke coefficients, Fourier Hecke coefficients, APF. And one would like say that P, the set of primes P, so that P divides APF, this collection is finite. Kind of what may be called supersingular reduction or non-ordinary reduction. This set of primes should be finite. And again, these things are completely open. It's not even clear how to approach these questions. Okay, so that is the thing. And Ser's motivation is to try to produce at least some evidence towards this to show that the set of primes for which say APF is non-zero or whatever it is a large set, and similarly to try to answer these questions. So that was Ser's thing. So let me say, so what Ser's approach is to use Galois representations. Yeah, no, okay, I should say, of course, non-CM. Yeah, thanks. Yeah. Non-CM. Right. So use Galois representations. And point is, when you are working with the eigenforms and of course in the elliptic curves, so you have the Galois group, in this case GQ, but let me say K is a number field. But more generally, I'll just take that. And we have GK is a absolute Galois group. So you fix a Galois closure and then, which is Galois group of E over K, all E which is contained inside K bar, and E over K is Galois. So you take an inverse limit, and so what one knows is that in this case, by theorems of various people, but finally by Delin, that you have a Galois representations attached rho from GK to some GLN of some L-adic fields, but let me just, instead of putting F, I'll just put QL. Okay, but you should basically, instead of QL, I should put F, but let me for this. Some L-adic field which is there. And yeah, these are some properties that one can look at the characteristic polynomials at the good primes. And if you take the trace of the Frobenius element at the good prime, that will be equal to the Hecke eigenvalue. Okay, so that's a property which you have, the trace of, suppose, let me say, rho f at a place sigma v. So let me say GQ. Frobenius at a good place is equal to AP of f. And there are other things which you can say, but this is, so what you have is that you have a Galois representation attached to this modular forms, eigenforms. And now once you have a Galois representation, this is, of course, this is a compact group, profinite group. So this lands inside GLN ZL or whatever it is, one can assume that. And so you can think of GQ to GLN ZL. And then this has various coefficients, finite coefficients. So you have various representations out here, and to count some kind of APF, which is a conjugacy class invariant function, because it's a trace, you can use, it defines a conjugacy class, so you can use Chebyshев density for this finite things. So then use Chebyshев density. And you can try to get results by controlling the error terms. The main thing is to control the error term, for which the theorems of Lagarias and Odlysko and Montgomery, maybe. So on controlling the error terms. So once you have this control on the error terms to some extent, then you can try to go into the limit as n goes to infinity and get some ideas about the distribution of this kind of conjugacy classes which are given. Yeah, so that is roughly what Ser's thing is and idea is, and he carries it over in this paper on some applications of Chebyshев density theorem. So what Ser shows is that so suppose if you work with E is a non-CM, so here also I should have said that these are all non-CM ellipticals. Meaning there are no extra endomorphisms. So, or or the representation is not induced from some subgroup in some sense. So, okay, use Stepetro density too. So what Serre shows out here, for instance, let me say this, is that, so then if you look at the primes p less than or equal to x, so that APE equal to is equal to 0. So this is basically is what would be called as little o of x upon log x. That means that divided by this pi x, the number of primes goes to 0 as x goes to infinity. Okay. So the density is, so what you can talk about is, one can talk about density, the usual probability density. You can look at density. You can define it as a set of all p less than or equal to x, so that say AP equal to 0 divided by the number of, this is the probability density p less than or equal to x. So if you work with E is non-CM, so E is non-CM, so then this density is, of course, one has to take a limit as lim sup or whatever it is, as x goes to infinity. So this density is 0. Okay, and then yeah, so in general, one can try to do it for, as I said, in the Galois theoretic setting also. I'll come to the theorem specifically when I want to say it. What he talks about in the Lamer conjecture, so this is what he says is so we would call this is as non-lacunarity. For primes, although Serre doesn't use this terminology, non-lacunarity for primes, but we'll use this. So what one is saying is that almost all, that is at a set of primes of density 1, which is the full density, with probability 1, AP is non-zero. Okay, so that is, if provided, of course, E is non-CM. The second thing is we want lacunarity for the non-lacunarity for tau n. So here, of course, what you would like to say is that, so for integral coefficients, again, you can look at set of all, say n, let's say tau n is non-zero. Of course, this is just you have to divide by x. And now we can take lim sup as x goes to infinity. Yeah, so what Serre shows, but this follows essentially from this statement that, so this is from here to here. Of course, this is for elliptic curves, but what I mean is for the, so if I, from rho delta, if I use it, and plus tau variant. So it follows from that this is some constant. Some constant C, greater than C. Okay, so in other words, what he's saying is this is like C times X. This is like C times X. Yeah, that a positive proportion of for integers n, tau n is non-zero. So this is shown by Serre. This, of course, follows from the prime theorem, which is there. Okay, so that is the background which Serre does. So now what I want to say is, so I forgot to say that this is joint work with Mihir Seth and Rishabh Agnihotri. And I don't know whether I should, this thing, I heard that Mihir is going to join here in 31st of Meir joint with yeah. So now, uh, so the question now is to extend some of these results to linear combinations of LS. So let me say LS rho. So I should say, so I've given a Galois representation, say rho from GQ to say GL and QL. You can attach what is called the L function of rho, which is a product for various primes P of, so as I said, for almost all representations, it's unramified, so there will be a Frobenius conjugacy class. So it's a characteristic polynomial of the Frobenius conjugacy class. Times P to the power minus S inverse. This is like the Euler product. Of course, at the bad places, you'll have to take the inertia group invariance and work with that. But anyway, basically, we have some L function, which I will write it as summation an by n power s, a rho n. Okay, these are the coefficients which. These are the good place, but okay, let me not complete what the definition is at the bad places. But so what we are interested is, in some sense, the behavior of a rho n as we want to do it. And what the results of Serre is saying is he's working with eigenforms, and the eigenforms correspond to Galois representations. And so you're working with a single Galois representation and getting it. But there are many modular forms which you get, for instance, the theta functions, which are not eigenforms in general. So the theta functions, theta modular forms, whatever it is. So these are not eigenforms in general, but only linear combinations of eigenforms in general. So if you want to, there was a paper of Choi and Kim, which tried to talk about theta functions and whether the Fourier quotients of theta functions determine the theta functions uniquely. And so they were saying that if you know that the Fourier quotients are the same for all but finitely many, and then that too of level 1, then in some sense the theta functions are determined. So our immediate provocation was to generalize that to a more general theorem. So the point is that what theta functions are, the space of modular forms as a basis consists of course, old forms and then new forms, assuming the level is square free or some technical conditions. Then you know that there is a basis for consisting of new forms essentially. And so I can write a theta function, say of square free level, as a linear combination of, if I look at the L function, of L functions attached to Galois representations, right? Because the new forms have Galois representations, so you can work with that. And the theta, the Fourier quotients can be expressed in terms of Galois representations. And then you would like to prove this kind of results which you want for linear combinations. So that is a first aim. The second aim, which I only thought about only yesterday, because I was sitting there and saying, okay, this is a conference in algebraic geometry, algebraic varieties. I need to say something about algebraic varieties. And then I realized there seems to be a nice application to zeta functions of algebraic varieties, in the sense of, because they can be written as, in terms of L functions, at least attached to Galois representations. And so you can ask for, if I want to know the zeta functions, again, zeta function is really a Dirichlet series, and you can try to look at the number of points of a variety defined over finite fields. Suppose if two such varieties are, the APs are linearly related, or because one would like to say even polynomially related, whether then the varieties are polynomially related, whether motivically or whatever it is. So there seems to be some kind of this thing, but I don't know. So I should still say it's a work in progress. But yeah, so thanks for the invitation again. That this. But anyway, so there are a couple of applications which this thing, but let me not come to the application, but say what the theorems are we have. So what we are looking at, so I'm fixing a number field K is a number field. And F is the local field of characteristic L, residue characteristic L. Of course, characteristic 0 and residue characteristic L. And I'm looking at continuous Galois representations from GK to say GLN I F rho I. And I can look at, so I'm looking at combinations like summation Ci, LS of rho I. And so I'd like to look at these coefficients of this, either the integral coefficients or the prime coefficients, and talk about lacunarity or non-lacunarity. Okay, so the theorem 1 is that so I have this kind of setting. So I need to say somewhere about non-CM forms, which has to be brought in. So assume, say for instance, yeah. Okay, so let me, so what I'm going to use out here is, when I'm working with Galois representations, I'll be looking at what would be called the algebraic monodromy group. So it's easier, rather than just the image of the Galois group, which is an L-adic is an analytic group. It's better to work with the algebraic monodromy, which is the smallest Zariski closure, let me just say, inside GLN of rho of GK. So this is, I will call it G rho. So this is my rho of GK. And the difference between, for instance, CM and non-CM, as far as these matters are concerned, amounts, you see, suppose if rho is non-CM, say n equal to 2, GL2, then 0 is GL2, and the CM case, so 0 is your normalizer of a torus. It can be a torus also, either NT or T. Yeah, maximal. So, so the difference is, in these cases, is actually when I'm working with the normalizer of the torus, is the fact is that this group is not connected, and that's what plays a role. Okay, so that is, I think so. What we are going to assume is that, to avoid the CM case in some sense, of course, there are various assumptions which you are going to make. Assume that G rho 1 is connected, I'll first give the slightly more general statement. That is one. Oh, sorry. Yeah, okay. Thanks. No. Each representation this is the monodromy of the thing. Of course, I will look at the Zariski closure inside the product soon. That is definitely, yeah. All right. Yeah, that's a standard. Yeah, right. 0, 1 is connected. And then I'll say that for any finite extension, any Galois extension, finite Galois, L over K, finite. I'm going to assume that yeah. Yeah, rho is not isomorphic to rho one, tensor some character chi. Oh, sorry. No, I just want to say that. Yeah, no, not this. I'll let. So, yeah, so I want to say that Hom GL, rho I restricted to GL, rho 1 restricted to GL is equal to 0. Yeah. So there is there is no intertwining map between when I restrict it to any subgroup of finite index, right? So then the set of primes P such that summation Ci A rho I AP A rho I A rho I of P is non-zero has density 1. Okay, so that is a before I go to the integral non-lacunarity, so let me say some words about the proof of this theorem. So the proof and then I'll come to the integral versions of this. Okay, so the proof, it depends on two facts. One which was proved by, so it depends on two facts basically. One which basically it's almost there in Sayre's paper, but he had not stated it. It's there in my what we call as algebraic Chebyshев density theorem. So let me just say what the usual Chebyshев density theorem says, that suppose if I have a Galois group of L over K, say this is finite extension, and so of course you have the Frobenius conjugacy classes at the good primes as K varies, and if you count, if you fix C is a, so this is my, say the Galois group, C is a conjugacy class, say Galois group of L over K. So I'm going to, this is Chebyshев density, usual Chebyshев density, usual Chebyshев. Okay, so let me say it in words that the Frobenius conjugacy classes are equidistributed with respect to the projection of the Haar measure on the conjugacy classes. So you have a map from G to G mod conjugacy. And in some sense, of course, one has to work with closed conjugacy classes in the analytic setting. But for finite groups, what you're saying is that the probability that some Frobenius element lies inside a conjugacy class is equal to the relative size of the conjugacy class. So if you fix C is a conjugacy class, then the number of primes V, a finite place, say norm V is less than or equal to X, and of course, I'm assuming it's a good prime, V finite good prime. We only finitely many bad primes. Sigma V of this L over K belongs to C, is equal to C. The conjugacy class is contained inside C. So if I count this number, so this is, and let X goes to infinity. Cardinality C by cardinality of G. Where G is this Galois group. Yeah. Okay. Okay, there are some error terms also. As I said, the error term has to be kept in mind if you have to carry out such thing. Okay, but let me say what the algebraic Shabatrov density theorem is. If I work with so I'm working with rho is general representation instead of a finite representation. So I'm looking at rho from GK to GLN F. And G rho is a algebraic monodromy group. And instead of, so you have to take a conjugacy class. C is of course, an invariant set. Algebraic is an algebraically closed algebraic invariant set. Invariant under conjugation. This is a conjugacy variety in 0. So then you can ask for the number of places V so that norm V is less than or equal to X, same thing. So that sigma V of L over K is contained inside C by say norm V less than or equal to X times pi of X. So this measures basically the number of connected components, number of G phi connected. These are connected components. So let me say number of connected components. Of 0 contained inside C by the total number of connected components, G upon 0. 0 upon 0 naught. So the point is that the usual Shabatrov density theorem goes over into the case where this is only for finite quotients, but you can work with any L-adic representation and work with the algebraic monodromy group. And as long as you assume that the conjugacy class is an algebraically closed invariant subset, that is invariant meaning it's a conjugacy class, and then you count the number of elements for which the conjugacy class lands inside C, if it is this thing, that counts the number of components which is contained inside. Okay, so that allows us to use algebraic methods to count as long as your conjugacy class is decent enough. And here our conjugacy class in the usual case is C is basically the set of all elements for which trace of G equal to 0. That's in the standard case out here. So here, of course, I'm going to take summation Ci times trace of rho I is 0, but inside the product monodromy group, right? So I will look at rho 1 cross rho 2 cross. I don't know how many representations I took from say rho R I equal to 1 to K. cross rho k. So that's my rho. And so I will try to look at the algebraic closure inside G rho. Right? And that would project to each of the monodromy groups here. So that's the first fact which you do. The second fact is a bit of relative Clifford theory. Which constant? No, yeah, but I'm going to take the condition, not this, but summation Ci trace of rho A of G equal to 0. Yeah, as long as I'm working with the trace things, which is so that's a advantage of working with the algebraic formulation, which is that you get this. Okay, the second thing is which goes into this is what would be called relative representation theory or Clifford theory. So what we have is that I have n is a normal subgroup inside G. Say G mod n is finite. So I can work with compact groups. G mod n is finite. Say G compact. And so suppose if I have two representations, say rho 1, rho 2 of G, and assume that form n rho 1 restricted to n rho 2 is equal to 0. Right? So then what happens is I can, suppose if I take n is trivial, if n is the full group, then I'm saying, and rho 1, rho 2 are irreducible representations. I'm saying they are distinct. Then we have the orthogonality relation for characters. And what we want to say is that if I take any cosets A, B in G, and chi rho 1 restricted to NA, the inner product chi rho 2 restricted to NB, this is equal to 0. Okay. So now if you use these two results, basically this theorem comes out. Okay, it's not too difficult to see this because finally on one of them rho 1 is connected. You will check that chi rho 1 itself has to be 0, which is not possible because rho 1 is connected. So anyway, so I'm just saying these two results will give you this non-lacunarity for primes. Okay, but now let me get to the integral non-lacunarity, which is also interesting in this sense. There's a very beautiful argument of Serre. He does it for. Yeah, so now integral, what I mean is this is for general coefficients n rather than only prime coefficients, integral non-lacunarity. For linear combinations. Yeah, so what Serre does is Serre proves it for only for GL2 over Q. Meaning he is working with, so suddenly he switches over to the modular form side, the analytic side. He is forgetting Galois representations. He uses the fact that you have a theory of Hecke operators and so yeah, so what he does is he uses Hecke theory. To prove a non-lacunarity for linear combinations. See, as I said, if I work with eigenforms, then it doesn't matter, you're working in the Galois theoretic setting, as long as you're working with one L function, then there is a non-lacunarity theorem, which is true if you're working with, okay, so I want to say, suppose if you, okay, so let me say the following. I'm going a bit far ahead. I want to say in case when 0 is connected, right, then basically you can't have a conjugacy, the entire connected component cannot land inside the trace equal to 0 because you know that identity, the trace is the dimension. So you know that the connected component cannot, so the set of places for which the prime P vanishes, AP vanishes, is a closed subvariety. And so the density has to be 0 by this kind of result. Okay. As long as 0 is connected, the algebraic monodromy is connected, then the set of primes for which AP is 0 has to be a proper subvariety of G, 0, and that has to be density 0. It can't contain the full connected component. Okay, so from there, a Tauberian argument gives you integral non-lacunarity. But now I want to go for linear combinations. Here, Serre uses Hecke theory for GL2. And this. So what, of course, Hecke theory, in some sense, is equivalent to giving an Euler product. And so since our Galois representations are by definition have an Euler product, so you should be able to, you can reverse engineer this, and the fact that it has an Euler product, you can develop a Hecke theory using theory rules to get at non-lacunarity. But there is a, so that is one proof, but I will not get into that. So yeah, but one can do it much more directly. So let me say the theorem 2. So I'm going to assume ρ1, ρ2 to ρk, and each ρi is connected. 0 is connected in the sense of the algebraic monodromy is connected. I don't know whether I need to assume this is enough, I think. Yeah. So then, so I can't, what we can say is that the limb sup as x goes to infinity of summation Ci. So let me use, although I'm working with n, so I will an rho I. Here n is an integral ideal in OK. Okay. It's non-zero. Yeah. Upon x, which is the thing. So that is positive. So this is the theorem which Serre proves in GL2 using Hecke theory over Q. I think Nekovar proves it for Hilbert modular forms. Again, uses once you have some Hecke theory or something. But yeah, so I should say when I'm saying Serre proves it for GL2 over Q, he is assuming that ρ1, ρ2 to ρk are the Galois representations attached to these forms. So basically, you're working with F1, F2 to Fk, each Fi is a non-CM form, and it's an eigenform. And so that is what. Yeah. I'm assuming at least one of them is connected. Okay, if I am assuming all of them are connected, I'm basically saying that they should not be twists of each other by a character. No, but if I'm assuming, say, basically, I'm assuming that the algebraic monodromy of the Galois representation, suppose if they're all connected, right? And the representations are not twists of each other by a Dirichlet, by a character, then this theorem is valid, right? But Sorry. That I need to know that the representations are kind of disjoint. Suppose if they are twist of each other by a character, then I can take a finite order character. Then that is a positive set of primes on which these things will be vanishing. Sorry, I don't still get here. I still don't get, yeah. Yeah. That is what Serre does. Serre does for GL2 rationals, meaning he's working with eigenforms, non-CM eigenforms, because I need this connectedness. Here too, for any L-adic Galois representations as above. In the sense, K is a number field, forget this. This I can think of it as GL and QL. F is a dummy variable. Yeah. Where is Q? Q is replaced by a number field K. GLN QL, L-adic. Yeah, so then what happens is you don't have too many continuous representations. You have only what are called weight zero representations. In which case, because this is a profinite group, the image is always finite. So then it is the usual Chebyshev density. Yeah, so in that sense, this is profinite and this is what do you call subgroup which has no small subgroups. So then it becomes finite. Yeah, so the proof of Serre is really, I just left wondering how he thought about the proof, but so basically what he says is, I have assumed this connected. So he takes the finite dimensional vector space. It takes the finite dimensional. So let me say what the proof is. So it's an adaptation of Serre's proof. I'm not this thing. Finite dimensional vector space. Of this LS rho I in the sense of formal finite dimensional generated by the LS rho I's, right? And now, as I said, the Hecke operator acts by multiplication for this thing. So I can write for each P, TP of Fi is Fi meaning rho I. I can define it as A rho I, say A rho I Fp times Fi. That's basically what the Hecke operator does. It's just multiplies by this. Okay. So so these are the basis for these functions. On each LS rho I, TP acts by multiplication. So these are semi-simple. This is a diagonal, so this is semi-simple. And the algebra they generate is commutative. Okay, so of course, at some point of time, I don't know. I don't think I need to go to complex numbers, but anyway. Okay, right? So you have this. Now what you check is that this condition that this is equal to 0 is preserved under the Hecke operators. This is a subspace. So the point is that let L. So let me say there is a finite dimensional vector space U, which is a formal linear combinations of those spaces. Let L be the subspace of U consisting of lacunar series. Then what happens is, so what you show is that L is stable under this algebra. So this, let me call this algebra. L is stable under action by H. First of all, it's a subspace. That is not too difficult to say. L is a subspace. If you add two lacunar series, lacunar, but it's also stable because you're just multiplying each function by some coefficient, and the lacunar series are going to be preserved. Okay, so L is stable at the interaction of H. Of course, for this I have to kind of say that the set of primes for which this is 0 upon the coefficient is 0, that see, this is in some sense the fact it's so this follows from what I would say is the linear independence. You see this the fact that every group is kind of so linear independence of the characters. They can't they have to on sets of positive density, whatever it is. Okay, so then what happens is, because it's a semi-stable algebra, so then there has to be an eigenform. And then the eigenform has to correspond to one of the Galois representations, because these are all different eigenvalue systems. But here we know by Tauberian theorem that they are non-lacunar. So that's what Serre uses to prove this non-lacunarity. And you can adapt this argument, say either you can try to mimic the fact that there is an Euler product and construct the Hecke algebra via the Pierre relations, or you can try to, I think this also is true. So the application to theta functions, it follows, it's not too difficult. As long as you're working with square free level, then and you're looking at linear combinations, at least I'm working with GL2. So then, or number fields, or totally real number fields. So then, yeah, so you can apply this to get a non-lacunarity for the theta functions. But as I said, I think it would be interesting to extend it also to algebraic varieties. There is one other application which you have is when you're looking at induced representations from K over Q is a normal, finite normal extension. You can try to look at the induced representation, which is you're taking a Dirichlet series and looking at it as a series indexed by natural numbers, which is there. And so again, if you assume that the representation rho sigma is not rho is absolutely irreducible connected, and rho sigma is not isomorphic to rho, then the induced representation has a correct non-lacunarity property. So you can, there are some applications which are there. I think it would be interesting to go from linear to polynomial relations, but I don't know. That would be fun to do, but it is anyway. Yeah, I think I'll stop here. It's a formal linear combination of the formal series associated to LS rho I. Each one of them is a basis for the, yeah, where this thing is 0. This lim sup is 0. This I would say is non-lacunar, right? That there is a positive proportion of n's for which A and rho I, the linear combination is non-zero. It's non-lacunar. Yeah, right. Fixed linear combination. Yeah. That doesn't matter. It doesn't. Yeah, as long as, see, all of them are anyway contained inside some GLN, so it doesn't matter. in the sense of, I have to say what is that I'm looking at something like a trace or some conjugacy class which has to be algebraic and invariant, right? And I'm trying to look at linear combinations in. Yeah, true, but that's what. So right now I'm working with linear combinations of traces, but yeah, that is enough. Yeah. Yeah. Right. Rather, or if that is too difficult, what you only get is x over log x to the power 1 plus delta. Yeah, that is all you can get. I have no idea. That would be the refinement of Lang-Trotter, which you probably have in mind. Yeah. You mean conjecturally, one should be able to say of what Lang-Trotter is. What is the power of x power a? Yeah. To whom are you? Akshay. Well, right. Yeah, so yeah, right. I suppose what I should also do is to work with the error terms also with the Chebyshев density and get slightly more the exponent of log x to the power 1 plus delta, which I think should follow to some extent, but yeah, that is, yeah, still, yeah, thanks. Right, but right now I would like to see if I can say something for zeta functions, because that the zeta function is a product of L functions for any variety. So then, in the sense, it's a virtual product, which is what I want, right? So that is exactly the kind of situation which you have. So in some, see, Serre does in that book NXP, he says that suppose if you have two varieties and you know that AP for large enough P of one variety and the number of points in the other variety differ by at most one, then he says basically they have to be like twist, there has to be a multiplication by some quadratic character or something. I don't understand, but yeah. So there must be some things which one should be able to extend that for linear combinations, but it would be interesting if you can say it for polynomial things, because then one can get into a motivic setting. That relationship between the Galois representations should say a relationship between the, on the level of cohesion should say some relationship between the Galois representations. But should be, yeah, anyway. But that is pure speculation. That is, I don't think polynomial will be too difficult. Okay,
Are there any other questions? If not, let's thank our speaker again.
Oh, thanks.
So before the cultural evening, there are tea and snacks in front of the auditorium. Light. At 5:30, there is a cultural event. 5:30, I mean 5:30, 5:45. Yeah. And then we will felicitate Kapil there. So if you want to take a hello. Excuse me, attention. Hello. So there is a cultural evening from 5:30. Okay.